Okay, I'm sorry for this delay. Okay, hello everyone, and welcome to NOUS Conference 2026, the International Conference on Infrastructure as a Service and Platform as a Service, solution for Europe's next-gen cloud infrastructure. My name is Gaetano Ladelfa, and I am the program chair of this conference together with Javier Prieto. And I work as a researcher at the Core University of Enna in Italy. Thank you all for joining this online event. In the next few minutes, I will give you a quick overview of the conference, the scope, the program, and how the day is organized. Okay. Just a few pieces of information. We will follow the Central European time, and the conference, as you know, will take place from 12 p.m. to 6 p.m. The day includes 3 technical sessions and 2 short breaks, one from 1:45 to 2 p.m. and the other from 3:45 to 6 p.m. The conference is fully online and the participation was free of charge. Please keep an eye on the time so we can more or less respect the schedule for all the speakers. And please put your name and surname on Zoom. The chair of each session will help you with moderation. Before we start, just a quick reminder about the context. NOUS is a Horizon Europe project which aims to build a federated and sovereign European cloud ecosystem that blends together edge computing, HPC network, and quantum resources. NOUS is designed as an open source architecture, and it connects with major European initiatives like Gaia-X or FIWAR. The conference is about IaaS and PaaS solutions for this cloud infrastructure. Today, you will see work across 4 thematic areas. The first area is about federated learning and federated edge cloud architecture. The second area is about AI across the continuum. The third is about data spaces and governance. And lastly, the fourth is about trust and resilience. These areas are organized into 3 technical sessions. Okay, we received a total of 30 submissions. Out of these, 19 papers were accepted and 10 were rejected because they were outside the conference scope and topics. 1 paper was withdrawn by the authors, and this gives us an acceptance rate of more or less 63% over all submission. And if we exclude the withdrawn paper, the percentage is about 65.5%. The review
Sorry, Gaetano, to interrupt. I don't think you are moving to the next.
Yeah. Sorry. Okay. The review process was single blind, so the authors didn't know the identity of the reviewers, and each paper was reviewed by at least 2 independent members of our program committee. A reviewer had 4 weeks to complete the evaluations. Another information that the accepted papers will be included in the ACM conference proceedings. I want to take a moment to thank you all the reviewers and the 39 members of the program committee for their work, because without their effort, this conference would simply not be possible. So thank you. In this slide, I show the full agenda for today. We start now with the opening, which will be followed by 2 short presentations by Carolina Villoria that will present the NOUS project, and by Yeray Mezquita that will present the Smart Data Space Innovation Center. Both of them are from Air Institute here in Spain. And then we will have 3 technical sessions. The session 1 runs from 12:30 to 1:45. And after a short break, the session 2 runs from 2 p.m. to 3:45. Then another second break, and the session 3 runs from 4 p.m. to 5:45. And finally, we close at about 5:45. So please, again, keep track of the time so we can respect the schedule for all the speakers. Just few words about the sessions. Session 1 brings together contribution on edge intelligence and distributed systems with a focus on federated learning, trustworthy decentralized infrastructure, and data-driven innovation across the IoT edge cloud continuum. We have 5 papers in this session, which is chaired by Celia Boulanger. Sorry for the pronunciation. And then we have session 2, which is chaired by Selini Hadji-Dimitriou, that presents 7 contributions on federated and edge AI for connected mobility, cybersecurity, and robust real-world perception. This is our largest session with 7 papers. The third session is chaired by Ricardo Alonso and brings together 7 contributions on trusted data spaces and governance, spanning privacy-preserving data sharing, blockchain-enabled accountability, regulatory compliance, and interoperable infrastructure across mobility, industry, and emerging digital ecosystem. Let me take a moment to thank the people who made this event possible. First of all, the General Chair, Ricardo Alonso from Air Institute in Spain. And then Javier Prieto, which is the program chair together with me. And our 3 session chair that are Celia Boulanger for session 1 from Politecnico di Torino in Italy, Selini Hadji-Dimitriou for session 2 from Università degli Studi di Modena e Reggio Emilia in Italy, and Ricardo Alonso from Air Institute in Spain for session 3. Okay, I also want to thank the organizing committee, the advisory board, and all the 39 program committee members for their contribution. Thanks also to all the authors and the speakers for contributing to the program, and thanks to all attendees for joining online today. Thank you also to the NOUS partners, a strong European coalition of academia, research, industry, and open source communities with a combined expertise that makes NOUS a broad and multidisciplinary consortium with real-world impact. And then we are at the end of this short presentation. I will hand over to Carolina Villoria from Air Institute, who will give us a short overview of the NOUS project. Carolina, the floor is yours. I stop the presentation.
Thank you, Gaetano, for giving me the floor, and thank you for your presentation. Well, I'm Carolina Villoria, and I'm here to present NOUS. The mission of the NOUS project is to create another cloud that is open, sovereign, and interoperable, that integrates edge computing, high-performance computing, and quantum resources into a single federated continuum. Here we can see that the project started in January 2024, and it will end the 31 of December of this year. The partners involved in the project, as Gaetano said, we are 21 partners from 11 different countries. The agenda, or what I'm going to explain today, is going to be first the NOUS methodology, then the objectives, the architecture, the use cases, and finally the impact. Just a brief explanation. So the objectives we can see in the NOUS project are the following: are the technological framework development, where NOUS is enhancing its framework to link in Europe's HPC network with quantum computing, increasing computational capabilities. The data processing and standardization innovative, that is that NOUS designs a model for integrating data from physical and digital resources, optimizing edge-to-cloud computation, and standardizing data formats in virtual sectors and using data lakes. The European Cloud Service Architecture, which is that NOUS develops a European Cloud Service Suite architecture incorporating computational edge computing and data processing to enhance the European Union digital sovereignty. Also the dynamic collaboration platform, where NOUS creates a Living Labs inspired platform for knowledge exchange and data sharing, facilitating cross-domain collaboration. And the last objective is a strategic partnership for data sharing, where the NOUS partners with initiatives to boost data interoperability, aiming for seamless sharing and a cohesive European cloud service framework. Here we can see the NOUS methodology, which where we follow the guest methodology, where we just don't develop technology, we translate every technical output into measurable KPIs. This allows our partners to stay perfectly aligned on delivering economic and suitable value. Regarding the architecture, a federated model based on data space participant and data infrastructure participants ensures no single entity holds central control. This is the brain of the project. Our architecture is based on this federated model I already said. We think as the connective tissue for European data spaces, we utilize compute to integrate supercomputing, edge for real-time processing via fast flow and federated learning, and we wrap it all in a data layer based on zero trust cybersecurity model. Everything is designed to be audit-proof, traceable, and fully compliant with the European data regulations. So regarding the use cases, we aren't just theorizing, we are testing this in 4 critical sectors: the connective mobility, the energy management, the crisis management, and the scientific data. The methodology we use, as I already said, is the guest methodology. Regarding the impact, we have a sovereign infrastructure and an open, audit-proof, and federated architecture that minimizes dependence on external cloud providers. The cross-sectoral innovation, we don't provide the connective tissue that allows Gaia X framework and other initiatives to actually talk to each other. And the sustainability is by optimizing edge to cloud flow, the significantly reduce the energy footprint and of data processing, directly supporting to the Green Deal. We are now entering in the final phase of the project with resources focused on full-scale development. We invite you to join us in shaping the future of a sovereign, sustainable European data economy. Thank you for your time, and I will leave the floor to Gerai. Thank you. Did I stop sharing?
Yes, thank you, Carolina.
Thank you.
Thank you.
Give me 1 second, Geray. I will try to give you the access. Okay. Try now.
Hello.
Yeah, perfectly.
Yeah. Okay. It is. I appear on the screen. Yeah, that's nice. Everything. Okay.
We can see you and everything. Thank you.
You can see my presentation.
Yes, perfectly. Thank you.
Okay. Thank you very much. Okay. So first of all, I'm going to introduce myself. I'm Geray Mezquita. Sorry for my voice. It's not been the best day of my life, but I will try to make you affordable at least to hear.
Geray, you just muted yourself?
Yeah.
Why?
Okay, now we can hear you.
I don't understand why. What happened? Okay, just make me know if it happens again. Okay, so first of all, the data space that we are building is in Zamora, a very nice city here in Spain, full of history, quiet, nice. If you are looking for a relaxed weekend, I advise you to come here. Leave this aside. The welcome. This is the place where we work. No, not for me today because I am a little bit sick. But here in this space, we try to develop and improve what it is one of the most important things in today's industry. So, first of all, who are we? We're a data space that it is led by the Institute, and it is funded by the Junta of Castilla y León. Okay, I'm going to use the laser. It's much better. In this place, what our main focus is the data spaces in which our central aim is to improve artificial intelligence system because the today's industry, the reign of the data has shifted to a new paradigm. So in this sense, we are trying to improve the methodologies that can be used in this system, in this kind of space. So, as objectives, as my introduction, we want to improve local entrepreneurship in the city. Also, we want to attract talent and investment, and thanks to this beacon of technology, we hope to also bring a lot of feed forward to the field of the data spaces and AI in the industry, in the current industry. Why would we want that? Okay, this is the first problem, the first challenge of today's industry. We have data. We produce data. We produce incredible amounts of data, but the data is how to say, scarce, and everyone has its own format, its own way to work with it. So what this means? This means that we have a very big wall between ourselves and between the improvement of our industry. So, knowing that the data is the most valuable resource and that it is scattered and underused, what we want to do with this kind of project is to secure an environment to share them. Because if we share our data, we will be able to improve the different models, the different data, the different how would I say it? pipelines used to treat and to understand and to extract information from the data. So that's why I think it is the main focus of our company to improve in this regard, in this path. Okay. So, what is a data space? A data space is a secure digital environment. That's what we want to call it. Okay. In this environment, what we want is to share the data in a reliable way, and we will be able to generate collective benefits for everyone. For everyone that it is combining and fusing this information, merging this information. So everyone will be able to collaborate, will be able to improve, to extract information from this data. In this part, the key of this project is that each participant will retain control over this data, his data, their data, and will retain the sovereignty of it, while it is being able to be shared with everyone and be able to extract the information that it is needed for the current industry. In this sense, we will say that a data space is something like this diagram, where we have like a oniric part in the center, which will be the data space that will allow every consumer and provider in the industry to share, to experiment with the data, while they are the owners and the keepers of the data. That's it. That is the main point of this. Okay. In this sense, what we want to improve in this sense, and what one of the few steps ahead that we are doing is to decentralize it, the data. Okay, like now, current systems are managed by one entity, powerful entity usually, that will keep, sorry, that will keep the data custody. So in this sense, what we want to is to allow the people, allow the companies, allow the different entities in the industry to control, to be sovereign of their own data, while in the same way being able to, in an easy and affordable way for everyone, to share those data. So, in what we do in Zamora is basically the creation of integrated data spaces, artificial intelligence platform. What we want is to be able to access to all this data and also to use this data to create an AI platform that will be able to extract information, even though we will be able to, we plan to be able to create a generative AI platform with also parts of federated learning. That's why the main focus of this, one of the main focus of this conference in the NOUS project, regarding the NOUS project. So for us, as a way to end this presentation, this is where we are. We are after we have the platform, we have developed, we have been developed the platform. We'll be able to to make full traceability of the data that is stored in the platform, that it is shared in the platform with a blockchain, with also being able to connect different data sources. We've been able to translate to a common tongue, for saying that way, the data. And also we've been using standards, EU standards, that make the share of this information feasible. We will be able, thanks to those standards, we are able to create interoperability between different services. So this is the last step, what we are working on. That it is the the creation of the federated learning system, I don't think I have to explain it to all of you, because I'm sure that you are also expert in this topic if you are going to make a presentation today. But in a small way, I could say that in a similar way that the data space is able to to share the data between different entities. With the federated learning platform, we will be able to share the different models without allowing the data to traverse the internet. In that way, the data will be kept secure, while the information obtained from this data is going to be shared. So yeah, it's a very complementary way to put them together. And in order to not making this presentation any longer, I will be able to thanks you all for being there, to the Junta of Castilla y León for being able to fund this project, and also the institute that we are working on in this project, for being the leaders of this project. So thank you very much, everyone. I'm going to stop sharing my screen right now, and I will let you all continue the presentations. Sorry again for my voice.
Thank you so much, Eray. We hope you recover soon. Gaetano, back to you.
Yeah. The next session, start the session 1 with Celia Boulanger. And let's start with the paper. Uncertainty-aware federated learning for robust multi-sensor fusion in connected vehicle perception, the first one.
Okay.
I'm not
sorry,
sure.
I was on mute.
Maybe I changed the order.
No, the first one
Sorry.
by Javier. I just gave him the rights to share.
Javier?
Yeah, he got the rights, I believe. Javier Manso.
Should I start to share it? Wait a minute. Are you watching my screen?
Yes, we do.
Okay. So, good morning, everyone. Today I will present, I will present our work title, Privacy Preserving 1 Hour Ahead Solar Power Forecasting via Federated Learning. Solar power forecasting play an important role in grid stability and energy markets. However, most modern approaches require collecting data from many different sites in a central location. In this work, we study whether federated learning can achieve competitive prediction performance while keeping data locally stored. Solar energy production is highly variable because it depends strongly on weather conditions such as clouds, temperature, or humidity. Because of this variability, accurate short-term forecasting, especially 1 hour ahead, is essential for energy dispatching and load balancing. The deep learning models, especially LSTM networks, have shown very strong performance for this task. However, this model usually rely on centralized training where data from any solar installation might be transferred to a central server. This creates important challenges related to privacy, data governance, and communication cost. For the reasons, we explore federated learning as an alternative approach. Previous research shows that evolution in forecasting methods. Early approaches were based on statistical or traditional machine learning models. Later, deep learning models such as LSTM and hybrid CNN-LSTM architectures achieve higher accuracy because they can better model temporal patterns. However, most of these approaches assume that all data is centralized. Recently, federated learning has been introduced in energy systems to enable collaborative training without sharing raw data. It has been applied to energy consumption prediction, solar generation forecasting, and anomaly detection. Despite this progress, several changes remain, especially in data heterogeneity between sites, scalability, and training efficiency. In particular, the relationship between federated on scale and prediction performance is still not fully understood. In this work, we have a solar forecasting task, and the objective is to predict the solar power production for the next hour using information from the previous 24 hours. This 24-hour lookback allows the model to capture daily production patterns as well as short-term meteorological changes. Each client in the federated system represents an independent solar installation or data holder. Instead of combining all datasets together, each site learns locally while contributing to a shared global model. To evaluate the federated approach, we test different federation scales ranging from 5 up to 55 clients. The model uses several types of input information, and these include meteorological variables like solar irradiance, calendar information such as hour day, site characteristics, and recent production history. An important aspect of this scenario is that data across client is not identically distributed, meaning that each site follows different production patterns. To ensure stability training, we apply robust scaling independently at each client. All experiments use the same LSTM-based architecture to allow a fair comparison. The model consists of an LSTM layer followed by dense layer and dropout regularization with around 80,000 trainable parameters, and the federated setting is used with PEDAP aggregation algorithm. We run 10 communication rounds, and during each round, clients perform 5 local training epochs before sending model updates to the server. For comparison, we also train a centralized model using the same architecture and training configuration. This allows us to directly compare federated and centralized learning. To evaluate forecasting performance, we use 4 complementary metrics, RMSE, that penalize large prediction errors and highlights strong deviations, MAE, that measures the average absolute error and gives an intuitive view of typical performance, SMAPE, that evaluates relative error, which is important when production values are very low, and finally, R-squared, that measures how well the model explains the variability of the data. Using multiple metrics help us to understand performance from different operational perspectives. And now we move on to the main results comparing federated learning and centralized training. At the Federated scale of 30 clients, we already observe an interesting trade-off. Federated learning achieves better performance in terms of SMAPE, meaning improved relative accuracy across different sites. However, centralized training obtains a lower RMSE, indicating fewer large prediction errors. This is important because RMSE penalizes large deviations more strongly, especially during peak production hours. So even at this intermediate scale, we see that performance differences depend on the evaluation metric. There is no single approach that dominates in all aspects. When we increase the Federated size to 55 clients, the difference becomes more pronounced. Centralized training performs better in both RMSE and SMAPE, and this suggests that as the numbers of clients grow and the data become more heterogeneous, centralized training handles both absolute and relative errors more consistently. However, federated learning achieves a higher R-squared value. This is particularly interesting because R-squared.
You've got 2 minutes left. 2
Sorry?
minutes left. Yeah,
Okay.
you've got 2 minutes left.
Okay,
Sorry.
thank you. This is particularly interesting because R-squared measures how well the model explains the overall variability of the data. So even though federated learning shows larger absolute errors, it still captures the general production dynamics and temporal patterns effectively. Besides accuracy, runtime is an important factor for a real-world deployment. We observed that federated training time increases as the number of clients grows. Training takes only a few minutes with 5 clients and remains below 1 hour even with 55 clients. These results suggest that periodic retraining, for example, daily updates, is operationally feasible. Based on our experiments, a federated size between 20 and 30 clients appear to provide a good balance between performance and training time. In conclusion, our study shows that federated learning can achieve predictive performance close to centralized training for a short-term solar forecasting. However, results depend on both the evaluation metric and the federation scale. We also show that federated learning retraining remains feasible within practical time limits. At larger scales, data heterogeneity becomes an important challenge. Future work will focus on improved aggregation strategies and personalization methods to handle non-IID data. Thank you so much for your attention.
Celia, unmute please the mic. You should unmute the. Okay.
Oh, yes,
Thank
yes,
you,
but I
thank
was
you.
not allowed. Thank you.
Thank you. Thank you.
So thank you very much for your presentation, Javier. So we have time for a few questions. Maybe you can, or I don't know if people can talk or just give their question in the chat if they want.
Okay. They can write in the chat any question.
Waiting for questions. Maybe I will start with a small question for Javier.
Okay.
So, Javier, what would be your next step to further improve the federated setup?
We have tried with only one setting of the federated training, so we can try to change the architecture or the or the metrics or the settings of the federated learning system.
Okay. There are other questions? I think yes. From Fabio. So I will read it for you. What kind of federated aggregation algorithm have you used server-side? So Fed average. Have you tried to use any privacy-preserving method like differential privacy?
We have used only Fed average, and we have not focused on privacy preserving methods yet. So it's also a next step that we can do.
Okay. Okay, thank you. Other question?
Thank you, Fabio.
I guess no. So thank you again for this interesting contribution on federated learning, Javier. And I think we can now move to the next presentation.
Okay, thank you, everyone.
Thank you. So our second paper proposes a fully decentralized learning framework combining blockchain and segmented gossip learning. The author introduced FedBGS, a system designed to eliminate the central server in federated learning while addressing scalability and non-ID data challenge. The presentation will be given by Fabio Turazza. So Fabio, the floor is yours. Fabio, we cannot hear you. Maybe.
Can you hear me?
Yes, now it's okay. Thank you.
Do you want to see my face as well?
Yeah.
Okay. Good morning again, everyone. I'm Fabio Turazza. I'm a PhD student from the Smith Department of University of Modena, Reggio Emilia. And today I'm going to present our work that's called the Blockchain-Based Framework for Segmented Gossip Learning, which is focused on a fully decentralized framework of federated learning for heterogeneous systems in terms of non-ID data. Why have we done this research? I think every one of you already knows what federated learning is. Basically, is a way to collaboratively train a model among various participants without sharing raw data. But federated learning, also known as basic Fed average, has three main problems, three main issues. The first one is a security issues, like it can suffer from different attacks, like poisoning, like civil attacks, like reconstruction attacks, which can lead to a degrading of accuracy and some kind of data leaks. The non-ID problem, and least one, but not the less important, the central server is treated as a single point of failure. That's why a lot of research works focuses on solve this last problem with gossip learning, with serverless federated learning, and with blockchain acting as central server. Our goal is to do a fully decentralized framework that preserves privacy and robustness, but still using blockchain and with sustainable costs. Our method is called FedBGS and is based on two pillars, like segmented gossip learning that's guided by dynamic clusters. Classes are formed by a federated k-means plus, like federated analytics, in order to cluster clients by label distribution, in order to segment the model for the peers, and an hybrid structure done by blockchain, Ethereum blockchain plus ePFS for verifiable history with low on-chain costs. our approach is done in order, we don't want to reach the state-of-art accuracy in our method. It's not our goal. We just want to have a complete framework which includes a lot of problem resolving, like non-ID data handling, hybrid storage, privacy preserving techniques, scalability, and the most important thing, we want a full decentralized system. I think is that a lot of current blockchain-based federated learning frameworks are using private blockchain. So they use full decentralization as a claim, but they are not 100% fully decentralized. This is the architecture of FBGS. It's composed by two different phases. We have a phase one with on-chain clustering, as I said before, by federated k-means ++ on label distributions. First of all, clients are registered by smart contract. We have two different kinds of smart contracts here, one for phase one and one for phase two. And then a model segmentation, where each cluster updates a single neural block of our CNN, because we have validated this on different vision tasks. Then we have a phase two with the real segmented gossip learning phases. Here we have the hybrid structure with IPFS for storage. What happens here in phase one? First of all, each peer computes the local label distribution. Then we have a one-shot federated k-means ++ aggregating centroids via smart contracts. That's a particular kind of federated analytics that's not federated learning 100%, because we aggregate centroids, not models. And then we have the cluster assignments. Why we do segmentation here? Because we want to have a faster convergence in order to have stable updates and to avoid the non-ID gradients conflict problem, because we want to also manage some heterogeneous clients. What happens in phase two? We have the real federated training with segmented updates and gossip exchange only within the assignment segments. Segments are coded on the second smart contract. We also have, as mentioned before, an IPFS storage with on-chain CID verification. What about the privacy preserving side? In phase one, we have used homomorphic encryption because it's not classical federated learning. Homomorphic encryption is also known to be heavy, to be computational. I think the heaviest privacy preserving methods at all. But we are sharing in a one-shot way only centroids, so we can use homomorphic encryption here. In the phase two, we avoid to use homomorphic encryption. We refuse to use it in order to use differential privacy and twin mean aggregation. This can lead us to avoid some problems like civil mitigation, like poisoning reduction. And we have a replay protection by the seed of IPFS plus blockchain. Why we want to use a public blockchain? Just because we want to have, as I said before, 100% system decentralized. And we want a neutral auditability across different organizations. Why we want to combine blockchain plus IPFS? Because we are using a public blockchain. So using a public blockchain, sharing weights and aggregate them on-chain will be costly. So we use IPFS, that's basically the centralized based system, as a storing layer. Here are the operation where we did on-chain and off-chain with registration, clustering, segment assignment, and incentives. And off-chain, we are doing the heavier computational operations like local training, segmented gossip, the storage, and the aggregation. So we want to use blockchain as a validator.
You've
with
got
the trust.
2 minutes left. You've got 2
2
minutes
minutes left.
Yeah.
Thank you. And IPFS scalability. These are our empirical results on different vision tasks on NIST variants like IMNIST, FMNIST, KMNIST, and NIST. What I want to show you is that, as you can see here, we are not focusing about the accuracy comparison with the state-of-art methods, but we just want to see that the system is already robust to non-ID data heterogeneity. We also have a performance on CIFAR10 and a table on blockchain cost analysis. How many times these operations are done and what kind of smart contracts are we using. As a conclusion, we think that FedBGS can be so impactful in terms of and can be so helpful for the NOUS purpose because it can be adapted to a lot of different domains, such as hospitals, factories, smart cities, but it could benefit even for some future works, future improvements, like to improve the scalability system by gossip learning and dynamic cluster adaptation, and to add some other privacy preserving methods. So thank you, everyone. If you have any questions, I'm here, or text me at this email.
Thank you, Fabio, and sorry for this time. I was still on mute.
No problem.
So thank you very much for this presentation. It was really interesting, and I look forward if someone has a question in the chat.
I'm watching the chat as well.
So let me start with a quick question. So small question and general, but how do you see Fed FBGS interacting in practice with existing data space infrastructure?
That's not an easy question, but I think FedBGS is a general purpose federated system, and it can be adapted for every kind of data structure we can consider.
Okay. Thank you.
For your question.
If someone has a question? Seems not. So I would like to thank you again for your contribution. And I guess we can move. Thank you. I guess we can move to our next presentation. So the next paper is about human-centered application of machine learning in smart environment. And this presentation will be given. So I think the speaker changed, and it's not Mahabuba Poroshmoni, but Halima.
Yes, ma'am, I am.
Okay. So
Kindly allow me to share my screen.
So we cannot, at least I cannot hear you well, Halima. Can you speak again to test?
Is it visible?
So we see your screen now?
Yes, is it visible?
Now we have your presentation, but about your micro, it's difficult for me to hear you.
Okay, ma'am, I am fixing it. Am I audible now?
Yeah.
Okay, ma'am. Thank you.
Thank you. So Halima, the floor is yours.
Thank you, respected chair. So first of all, I would like to introduce myself. Good evening, everyone. I am Halima Khatun Mim, an undergraduate student from Department of Computer Science and Engineering at International University of Business, Agriculture and Technology, which is located in Dhaka, Bangladesh. It is my pleasure to present our research titled Predicting the Thermal Comfort of Non-Academic Workers at University, a machine learning-based approach. This slide shows the outline of my presentation. First, I will begin with the introduction, where I will provide the background information about this research and explain why this topic is important. Next, I will discuss the objective of our research, and then I will explain the materials and methods, including how we collected the data and which machine learning models we have used. After that, I will discuss the key results and SHAP-based importance analysis. Finally, I will conclude the presentation with key outcomes and future recommendation. Thermal comfort is a key factor influencing occupational health, productivity, and overall well-being in indoor environments. In university workplaces, many non-academic workers such as maintenance and staffs and spend long hours indoors. However, the most previous research has focused primarily on office workers and academic staff. Therefore, understanding the thermal comfort condition for non-academic workers in tropical climate underexplored. The main aim of this study is to predict thermal comfort among non-academic workers using machine learning techniques. To achieve this aim, first we collected environmental, demographic, and perceptual data from participants. Then we developed 3 machine learning models: decision tree, random forest, and XGBoost. Finally, we evaluated model performance and identified influencing factors using SHAP analysis. So here is the materials and methodology slide. This study was conducted at a university campus during winter season from November 2025 to December 2025. We collected a total 200 samples from non-academic workers. The data collection process involved 2 main components: an occupant survey and digital measurements. Structured questionnaires were used to gather information on thermal perception and demographic characteristics. At the same time, digital meters were used to measure environmental parameters such as temperature, humidity, and indoor air quality indicators. In total, 21 variables were considered, including environmental factors, demographic characteristics, and architectural design features. After the data collection, the dataset was cleaned and pre-processed by removing outliers to improve model accuracy and reliability. The overall methodology of this study is illustrated by the right side of the methodology flowchart. First, the study area was selected, which was university campus in Dhaka, Bangladesh. Next, relevant parameters were identified, and including environmental parameters and demographic variables and perceptual thermal comfort indicators. After selecting the parameters, data were collected using structured surveys and digital measuring devices. The collected data were then cleaned and processed by removing outliers to ensure better data quality. After processing, 3 machine learning models were selected for prediction: decision tree, random forest, and XGBoost. The dataset was then divided into 80% for training and 20% for testing. Finally, the models were evaluated using accuracy, mean squared error, root mean squared error, and SHAP analysis to determine the future importance and interpret the model results. Thus, this slide presents machine learning models we have used in our study and evaluation approach. We applied 3 machine learning models to predict thermal comfort. First model in decision tree, which is a simple and interpretable model that helps understand the decision-making structure of the data. The second one is random forest. Which is an ensemble learning model that combines multiple decision tree to improve prediction accuracy and reduce overfitting. The third one is XGBoost, which is extreme gradient boosting, which is an advanced boosting algorithm known for its high predictive performance. To evaluate the results, we here use prediction accuracy and SHAP interpretability. Now I will present the key findings of our study. All the 3 machine learning models have achieved over 85% accuracy, indicating a strong predictive capability among them. The decision tree model outperformed the best, achieving an accuracy of 0.93 with a mean squared error of 0.21 and a root mean squared error of 0.46. These results demonstrates that machine learning models can effectively predict thermal comfort conditions among non-academic university workers. Interestingly, the simpler decision tree model outperformed best. Now, the slide presents the SHAP-based feature importance analysis for 3 machine learning models. Decision tree, first one is decision tree, then XGBoost, and then random forest. SHAP analysis helps us understand how each feature contributes to the model's prediction and improves the interpretability of the machine learning models. The first diagram of the SHAP analysis of decision tree model shows us that the location of the workplace, ACHO, clothing label, and using electric fan has the highest amount of importance. Then the second figure represents the SHAP analysis for the XGBoost model. In this model, carbon dioxide level, light intensity, humidity, and noise level are among the most influential features affecting thermal comfort prediction. The third diagram allows the random forest SHAP analysis. In this model, humidity, gender, wiring, and apron during the work and perceived resting comfort show that relatively higher contribution of this prediction. When we comparing the 3 models, we observe that humidity consistently appears as one of the most influential variables across all models, indicating its strong influence of thermal comfort perception. Additionally, environmental workplace related variables such as carbon dioxide level, location of workplace, and light intensity also play significant roles
Halima,
in
you've got 2 minutes left.
Okay, ma'am. Determining thermal comfort. Overall, the SHAP analysis highlights that humidity, carbon dioxide level, workplace location, TVOC, and light intensity are the key contributors influencing thermal comfort among non-academic workers. In conclusion, this study demonstrates that machine learning can effectively predict thermal comfort among non-academic workers. In tropical or subtropical university workplaces, SHAP-based interpretability allowed us to identify key influencing factors supporting evidence based on decision making. Our findings support the development of low energy, climate resilient indoor comfort strategies suitable for resource constrained campuses. In the future, IoT integrated with AI systems could enable real-time and adaptive thermal comfort in the future. Thank you for your attention. I would be happy to answer any questions.
Thank you very much, Halima, for this presentation. We have time for a few questions. Okay, but feel free to raise your hand or write your question in the chat. I have a first question for you, Halima.
Yes,
Do you think your model would behave differently if extended to other seasons beyond winter?
this is an insightful question. Yes, I highly believe that if we collected 2 seasons data, then the model performance may have increased.
Okay. Thank you. No more question? No. So I think we can close this presentation, and thank you again, Halima, for your presentation.
Thank you.
So we will start with the first presentation and now return to distributed energy system from an edge intelligence perspective. The presentation will be given by Julia Lopez.
Yes.
Hi, Julia. The floor is yours.
Okay, I will to present. Okay. Hello, good afternoon, everybody. My name is Julia Lopez from the University of Cantabria in Spain. I'm currently a master's student and a researcher in the TESA department in the university. I'm going to present our work under the title Virtual Sensors in Photovoltaic Inverters at the Edge, developed in collaboration with Paula Lamo, who is also from the University of Cantabria. Currently, most photovoltaic monitoring systems rely on centralized cloud-centric architectures that require the continuous transmission of large volumes of raw data. This approach does not scale effectively as the system grows due to inherent scalability and communication limitations. In this context, edge computing and virtual sensors emerge as a key alternative, enabling local processing, reducing data flows to the cloud, and improving overall system scalability. Photovoltaic infrastructures are becoming increasingly distributed with a growing number of inverters at measurement points, which significantly increase systems complexity. This continuous growth leads to a sustained increase in data volumes and communication requirements, making centralized monitoring models costly and difficult to scale. In addition, the high dynamic nature of PV systems requires a fast response, while reliance on cloud-based architectures introduce latency and limits the system's ability to adapt in real time. Today, most PV systems rely on raw data streaming from inverters to the cloud, where all analytics are centralized. As the system grows, this approach does not scale, generates massive data flows, increases cloud and communication costs, and creates a strong dependency on centralized platforms with additional governance and privacy concerns. So how can we address this limitation? Well, the solution lies in structuring intelligence at the edge to enable efficient, scalable, and governable energy monitoring. We must reduce data traffic, increase system autonomy, and ensure regulatory compliance. These requirements cannot be met through fully centralized architectures. Instead, part of the intelligence must move to the edge. Virtual sensors enable this transition by transforming grid-connect photovoltaic inverters into governable digital assets at the edge. So how do we implement intelligence at the edge without increasing hardware complexity? This is where virtual sensors become essential, and virtual sensors allow the inference of variable of interest from already available internal signals without requiring additional physical sensors. by liberating control observables or in-bid models. Virtual sensors enable monitoring, diagnostics, and event generation. In grid connect inverters, this approach reduces instrumentation and increases system visibility without modifying the power stage or certification requirements. Because this intelligence is embedded in software, it becomes inherently scalable and naturally aligned with an edge-oriented architecture, enabling a low-cost deployment across the distributed PV system. Instead of introducing additional sensing mechanisms, we exploit estimation structures that are already implemented in the inverter control firmware. By reinterpreting these structures as virtual sensors, photovoltaic inverters can be transformed into intelligent, governable edge devices. A clear example is the phase loop PLL. This is a mandatory component from synchronization and stable current control. From our perspective, the PLL can be interpreted as a virtual sensor. Beyond synchronization, the PLL generates internal observables such as a phase, frequency, and phase servo, whose dynamics reflect the grid converter direction. By exploiting these already available signals, we obtain compact and informative indicators without additional sensing or raw data transmission. And grid connect inverters operate under strict real-time constraints where control tasks dominate computing and latency budgets. As a result, edge intelligence must be ultra lightweight with bound execution and a strict separation from the control plane. Instead of heavy analytics or continuous streaming, we structure internal observable into compact indicator, full preserving control, determinism, and compliance. This approach not only addresses the internal technical constraints of the inverter, but also aligns with the European regulatory framework, which regulates observable behavior rather than internal architectures. This alignment becomes clear when examining the European regulatory framework. The first three regulations govern observable electrical performance at the point of connection. They don't prescribe internal control architectures. The EI Act introduced a risk-based classification. Science or approach is limited to supervision and diagnostics with no actuation capability. It avoids high-risk classification. The last two promote control data access and trust sharing by structuring compact event-based outputs instead of raw data streaming. We enable proportional and auditable data exchange. In summary, regulation governs observable behavior and data usage, not internal intelligence. Or edge-based supervision preserves certified control while enabling compliant innovation. In practice, this means rethinking how data is produced and shared at the edge. Instead of transmitting continuous telemetry, the system generates an event whenever a relevant condition is detected. Each event is accompanied by contextual metadata, such as the analyzed time window, firmware version, and model version, and active configuration. It also includes a reduced set to interpretable indicators that describe the detected state. This approach drastically reduces the volume of transmitted data while increasing evidential value and traceability, facilitating on-site verification of ultra-lightweight models. In large distributed energy systems, the dominant cost is not sensing, it is systematic data handling. Continuous high-road streaming scales linearly with flat side. Our approach shifts value generation to the edge by transforming internal signals into structured low volume and data products. This enables economic scalability, regulatory alignment, and trust participation in federated European energy data spaces. In conclusion, several challenges remain. First, semantic interoperability. We need standardized event profiles and common metadata structures. Second, implementation heterogeneity. Different PLL designs require operational invariance and comparable conformity tests. Third, cybersecurity. Exposing semantic events expand the attack surface and must be carefully governed. Finally, scalability ultimately depends not only not only on computation, but on trust and governance within federated data ecosystems. Addressing these challenges will define the next stage of scalable and governable energy systems. So that's all. Thank you for attention, and welcome any questions or comments.
Thank you, Julia, for this presentation and perspective. We have time for a few questions. Feel free to write them in the chat.
Okay. There is a question. No.
I don't see.
Okay.
It was the previous one. I'm starting.
Okay.
I'm curious, in fact. Do you know how close this approach is to industrial deployment in existing photovoltaic installation, in fact?
Maybe it's not in the industry now, but in some previous stage, maybe to implement a ultra lightweight AI in the PLL, but in industrial I don't think so.
Okay. Thank you.
Thank you.
Someone else? One question? Now we are perfectly on time, even early, I think, with the agenda. Carolina, do you think we can start with the last presentation?
Yeah, Nicola is right here, so I believe we can.
Okay. So thank you again, Julia, for this presentation, and we can start our final presentation.
Okay.
So this presentation will be given by Nicola Bicocchi. Nicola.
Yeah.
Okay.
I'm trying to share. Okay. Can you see it?
Yes, perfectly.
Okay. So good morning, everyone. I'm Nicola Bicocchi, and today I will present our work on integrating data mesh and data spaces to support distributed intelligence across the IoT edge cloud continuum. This research is part of the NOUS Horizon Europe project and has been developed in collaboration with my colleagues Rossini, Piccone, and Mamei at the University of Modena, Reggio Emilia. And we will explore the challenges of modern data architecture and how our approach enables trusted and scalable and distributed AI. And modern systems such as smart cities, mobility networks, and industrial IoT deployments generate an increasingly large amount of data, especially at the edge. And this creates a highly fragmented and complex environment where multiple stakeholders own and control different datasets. At the same time, real-time analytics and distributed AI are increasingly required to make fast decisions. And traditionally, solutions struggle to manage this complexity and to provide the necessary scalability and interoperability. And traditional data management are typically based on ETL pipelines feeding a centralized data warehouse or a data lake. And the data is extracted from different sources and transformed and loaded into a single repository where analytics are usually performed. And while this approach works well for business intelligence and best analytics, it introduces several limitations. First, everything must flow towards a central platform, creating bottlenecks and increased latency, and especially when dealing with high-frequency edge data. Second, even with the data lake, integration often remains complex and domain knowledge is lost, leading to data silos inside the central platform. And third, this model is not designed for distributed AI, where models need to run close to the data sources and sometimes collaborate through federated learning. And finally, centralization weakens data ownership because data ownership and control become blurred once information is consolidated in a single large repository. And for this reason, ETL-driven centralized architecture struggle to support recent scenarios. And our key insight is that no single paradigm is sufficient. And to manage data and AI at scale, we need two complementary approaches. The first one is data mesh, which enables decentralized management and processing within an organization, while data spaces allow trusted collaboration across organization. And by combining these two paradigms, we can achieve a form of distributed intelligence that is both scalable and secure. So the first one is a data mesh, which is used for organized data internally within an organization around business and operational domains. Each domain is responsible for managing its own data and for delivering it as an high-quality data product. This means that data is not just stored, but designed, documented, versioned, and made discoverable with clear interfaces and service level expectation. And in IoT edge cloud environment, this is particularly important because processing and intelligence can be moved closer to the data source, for example, at the edge, thus reducing the latency and network cost. Moreover, data mesh naturally supports distributed and federated AI because models can be trained or deployed across multiple domains without centralizing raw data. And overall, this paradigm enables each domain to operate with a high degree of autonomy while still contributing to a shared and interoperable intelligence ecosystem. On the other hand, data spaces focus on collaboration across organization, and as we already said, enabling different stakeholders to share data and knowledge while maintaining control over their own resources. So instead of centralizing information in a single platform, data spaces promote a federated architecture where data remains with the original owner, but can be accessed and reused under specified conditions. So a key aspect of data spaces is data ownership. So organization can define who can access their data, for which purpose, and under which policies. And another fundamental element is semantic or interoperability. So shared data is in fact enriched with common vocabularies, metadata, and ontologies, making it easier to integrate information from different domains, cities, or even industries. So overall, data spaces can be considered the foundation for cross-organization analytic, federated AI, and also collaborative decision making at the European scale. So to test this idea, and validate our approach, we used the modern automotive smart area, which is called also MASA, as a testbed. MASA integrates a smart mobility system, edge devices, and cloud analytics to explore how distributed AI and federated data sharing can work in a real-world urban environment. So we designed a data mesh architecture composed of multiple domains distributed across the IoT edge cloud continuum. Each domain manages its own data pipelines and exposes standardized data products, enabling autonomy while ensuring interoperability. At the edge layer, we have the smart camera domain, which ingests video streams and performs local processing, such as object detection and localization. Instead of storing raw video, it produces aggregated observation, reducing bandwidth and preserving privacy. Also at the edge, we have the VRU proximity domain, which detects a hazardous situation involving, for example, a vulnerable road user. And because in this scenario, latency is critical, inference pipelines run close to the data. And this service is also duplicated in another one, which is called AI domain, which does the same thing basically, but using deep learning. At the cloud layer, so in a different part of the network, the contextual data domain aggregates external information, such as weather and environmental condition, enriching downstream analytics and machine learning models. And finally, the MLOps domains monitor data drift and triggers automatic retraining when needed. And finally, the business intelligence domain consolidates prediction and contextual data in the cloud, providing dashboards and insights for stakeholders. And without the NOUS project, MASA acts as an edge intelligent node, contributing to federated knowledge-centric data space. Internally, the MASA data mesh produces and consumes domain-specific data products, such as proximity indicators, traffic flow summaries, and MLOps metrics. And finally, exportable products are then enriched with semantic annotation, provenance data, and usage policies, making them ready for trusted sharing across organization via the NOUS data space. And MASA can publish data using a NOUS connector, which handles authentication, authorization, data access contracts, and policy enforcement, and audit logging. And from the MASA perspective, the connector is a consumer of its own products, while the NOUS data space sees MASA as a certified provider. Typical consumers include regional authorities, other cities testbed, research institution, and even industry partners. Importantly, MASA retains the full governance over which data is shared, at what granularity, and under which condition, preserving local autonomy while enabling collaboration.
Nicola, you've got 2 minutes left.
Yes, I finished. In conclusion, integrating data mesh and data spaces allow scalable distributed AI while ensuring trust and interoperability between organizations. MASA demonstrates that this integration is feasible in a real-world smart city context. And looking forward, we aim to enhance this approach with eventual semantic AI and further capabilities in federated learning. Thank you.
Thank you, Nicola, for this presentation. We have time for some questions. Feel free to write in the chat. I will start with a quick question.
Okay.
Nicola, do you see this integration as something that can be adopted incrementally by cities, or does it require a full architectural design redesign from the start?
I didn't get the word. You said other cities?
Yeah. By cities, not other cities.
I didn't get the word. Before cities.
Incrementally?
Incrementally. Oh, yeah. Yes, I mean, we basically use the NOUS database concept, which can be implemented incrementally in other cities. The specificity of this work is that this architecture is matched with a data mesh within our domain. So we try to demonstrate that these two approaches can live together. But yes.
Okay, thank you.
No problem.
Thank you. Thank you to all presenters. Now, a short break before starting the session 2. And we will come back at 2 o'clock. Okay, thank you all. Thank you, Mark.
Perfect. Thank you so much, everyone.
Okay. See you later.
Thank you.
Okay. 2 o'clock, perfectly in time. Now we can start the session 2, which is chaired by Selini Dimitriou. Sorry for the pronunciation. Okay, the floor is yours, Selini.
Thank you very much for this invitation to chair this very nice conference. This is session 2 of Federated and Edge AI. Each presentation has 10 minutes, right? Okay, good.
Yes.
We think we should start already with the first one, uncertainty where federated learning for robust multi-sensor fusion in connected vehicle perception. Samuel Adrados.
Can you see the screen?
Yes.
Okay. My name is Samuel Ladrados, and I'm here to present our paper, Uncertainty-Aware Federated Learning for Robust Multisensor Fusion in Connected Vehicle Perception. This work has done with my colleagues Sergio Alonso Royan and Sebastián López Flores. And I will explain how we can make autonomous cars safer in bad weather by changing how the models understand uncertainty. Let's start with the basics. Autonomous vehicles use multiple sensors like cameras, radars, and LiDAR to see the world. Under perfect sunny conditions, it works great. But in the real world, we have rain, fog, snow. And in these situations, the cameras cannot see well, or the LiDAR's laser are scattered. So a combination of these with radars, which works better in adverse conditions, is recommended. Also, these cars generate massive amounts of data that is too demanding to send all this data to a central cloud. So the standard solution for this, and also to avoid violating user privacy, is using federated learning. In federated learning, the car trains the AI of the model locally using its own data, and then it only sends the mathematical average of the weights to the central server. However, current federated learning has a problem. AI models often have overconfidence. They make mistakes in bad weather, but they are very confident about those mistakes. So most uncertainty-aware federated learning solution penalize uncertainty. For example, when a car drives in the rain, its data has high uncertainty, and the central server tends to penalize or to reject its updates. So what happens with this? The global model only learns the cars that drive on nice sunny days or days with good weather. So we are throwing away the most critical safety data, the data from storms or night driving. And this can make the final model biased and unsafe. So to fix this, we propose a novel formula a novel method to ponderate, to weight clients. And also we train it with a new framework. First, on the left, we calculate epistemic uncertainty. This means that the model is ignorant in the new data. It happens when the car sees a new situation it hasn't learned yet, like a rare rain day. We want the global model to learn from this, so we can reward this data. And second, on the DS step, we calculate the aleatoric uncertainty, which it just calculate the physical sensor noise, like a camera lens covering mud, for example, or a camera that has some failure. The data is useless or is not that great, so we penalize it. Instead of rejecting everything, our cars send both of these uncertainties to the central server. So how do we actually calculate this? We use the mathematical approach developed by Kendall and Gall using Bayesian neural networks. During driving, the model updates. The model uses the technique, the Monte Carlo dropout, where we pass the same image through the model multiple times, and to find the aleatoric uncertainty, the noise, we measure how much the image confuse the model on every single attempt, and to find the epistemic uncertainty, the ignorance, we take the total doubt of the model and subtract the sensor to the noise. And the formula we use on the server dynamically weight the updates from the client. It multiplies the epistemic uncertainty to prioritize new scenarios, while it divides the aleatoric uncertainty to block the band sensor noise. To test our idea, our method, we use the nonsense dataset, which has synchronous camera, LiDAR, and radar data. We simulated an environment where it handles different weather. 6 cars drove on day or sunny days, 2 in the rain, and 2 at night. We then compare the standard Fed average method with our method, our proposed method. First, I must mention that as Bayesian network require heavy computation, we evaluate this at an early training stage. Therefore, the MIP is close to 0 because we didn't have enough resources. However, our main goal is to use to improve the model's probabilistic calibration, meaning that the model knows when to be confident and when to be careful. If you look at the columns for the negative log likelihood and the expected calibration error, there is an improvement, which means it gets lower in our method compared with
Samuel, you've got 2 minutes left.
Okay, so with our so to conclude, most federated learning systems penalize all uncertainty, but in driving, uncertainty usually means bad weather. So if we throw it away, we reduce safety. Our methods explicitly separate sensor noise from novel situation. This creates a dual role. It improves the model calibration and it helps the local car choose the right sensor in real time. And even at early training stages, we saw some improvements in NNL and EC. And for our future work, we plan to use more powerful computers to train our resources to train the model fully on the entire NOUS dataset, and this will allow us to evaluate it effectively. And that's all. Thank you so much for your time, and I'm happy to answer any question.
Okay, thank you. Can you hear me now? Yes. Oh, good. Okay, thank you very much for your presentation. I don't know if there is any question. Okay, I don't see any question at the moment. How your framework can take into account the fact that, I mean, during adverse weather conditions, the data degradation is a possibility, but not a given event, a certain event. So how do you balance different data degradation, or I mean, if it has already, if it is occurred or not? How do you detect the situation and take it into account in your framework?
We use the Kendall and Gal approach, where they measure it by using Monte Carlo dropout. Basically, it tests how much sensory data, how much noise the data has by getting the mean or the average of all those execution or all those instance of the model or inference of the model. So yeah, through that formula that it was already proposed, and then we just get the epistemic uncertainty based on or by subtracting it from the global uncertainty.
Very good. Thank you very much. I don't see any other question. So I think we can go to the next presentation, which is dual path, lightweight intrusion detection via PCA, and compressed latent feature and tiny gated MNPs. Mahmoud Abbasi.
Hello, everyone. Can you hear me? Okay, let me share my screen. Can you see the screen?
Yes.
Okay, let me. One moment, please. Okay, thank you so much for the time. The paper that I'm going to present is dual path lightweight intrusion detection using the PCA compressed latent features and also tiny gate MLP. During the presentation, I will try to provide a backbone and motivation, also talk about the key contribution, and also talk about the proposal method and result and conclusion. As you may know, the IoT network and also industrial IoT network provide a huge amount of the IoT traffic. So intrusion detection system have to decision continuously, and also they should be fast. At the same time, when it comes to the edge computing, I mean the edge devices such as gateway, they usually have strict, limited in terms of the computation, memory, energy, and also they have to provide low latency reaction regarding the task. When we look at the literature, we understood that the deep learning-based intrusion detection system can provide high accuracy, but at the same time, it's almost challenging to deploy this deep model at the edge devices such as gateway, because the deep model needs a lot of computation and also the memory and energy. One of the key observations in terms of traffic classification and monitoring is that many traffic flow are almost easy for classification, maybe because many of them are binary classification, and also just a small fraction of these network traffic are close to the decision boundary, or they are hard for classification tasks. So in this paper, one of the main goal is to focus on this challenge and provide a method that provide good accuracy close to the heavy models such as the deep learning model, and at the same time with the spend less computation and memory and resources. Regarding the contribution, we can refer that we provide a dual PaaS IDS architecture, runs a tiny edge model by default, and only pass the difficult network flow to the heavy model. Also, in our method, we use PCA in order to compress the features to the new latent space in order to keep the more informative data, at the same time remove the noisy information. Moreover, we provide a confidence aggregating. We use the maximum softmax probability as a simple way to score provide the confidence score regarding each flow sample. Moreover, we provide a much more faster method when we compare with the baseline and counterpart. This slide provides a visual representation of the proposed method that includes several steps, such as the data pre-processing, training the two different models, and also inference, and also decision. In the next slide, I will provide more detailed information about each of these steps. The first step is in our proposal method is to do a pre-processing on the incoming to the input traffic, such as converting features to the numerical value, replacing invalid values, filling missing values, and other pre-processing steps that usually we do for each machine learning task. The second step is train a heavy model. In our implementation, we train a full features MLP model on all the input features. The given model has two hidden layers, use the ReLU activation, and also a softmax layer to do the classification. The heavy model is stronger and also at the same time is larger baseline. The given model can provide more accurate result, but at the same time is slow and heavier because it's work on a full features space and also have more computation units. The second step is that we do apply a PCA or principal component analysis in order to reduce the number of the dimension of the input feature. For example, instead of using the original features, for example, 83 to 84, depending on the data set that we use for the evaluation, we project data to a smaller latent space. In our implementation, we use 32 dimension to decline the number of the features in our input. At the same time, we try to keep all more informative features. And the next step is to train a tiny model. On top of the PCA compressed features, we train a tiny MLP that has one hidden layer with only 32 hidden units, and also we use the ReLU activation in this case and softmax for the classification. So the tiny model is much cheaper. Next step is to use a confidence-based routing. For each network flow that the tiny model predicts a class for probabilities, the system then computes the MSP or maximum softmax probability, which is simply the highest probability among the predicted class. If MSP is greater than the threshold, greater than or equal to the threshold, we trust the tiny model and its prediction. If MSP is less than the determined threshold, we send the flow to the heavy model. So this gate in our paper means that a routine decision. I mean, if the MSP is higher than the threshold, we do not send the model to the heavy model when we trust to the tiny model. In this case, we can decline the computation and memory and energy we need for the classification of the traffic samples. Let me provide an example. Imagine that one network flow comes to the network, the tiny model
Mahmoud,
yeah.
You've got 2 minutes left.
Okay. For example, imagine that the predicted class in this case is DNS float, that the MSP is 0.78 because the MSP is less than the threshold, so the tiny model is not confident. So we have to send the sample to the heavy model, but for the final decision. So I'll skip this example because of the time. Here's two data set in our implementation. Also, we use some baseline model for the comparison. The first result is that we do some experiment to compare the performance of the the tiny model with the strong one. As you can see, the tiny model provides almost a comparative performance to the heavy model. The main reason of this experiment was to show that we use a strong tiny model as a baseline for our main proposed method. Also, in this experiment, we try to show that the tiny model, that the proposal model can provide almost same performance with a pure heavy model, only with a small escalation or processing the input data to the heavy model. For example, in a first data set, only with 2 to 5% of the passing of the network flow to the heavy model, we provide a performance almost close to the heavy baseline model. And also in the second data set, with the passing only 5 to 10% of the flow to the heavy model, we provide the almost similar performance to the pure heavy model. What I mean is that we can pass only something between 2 to 10% of the samples to the heavy model, but we provide a similar performance to the pure heavy model. Also, one of the results that we understood during the
time's left, so try to sum up a bit.
Okay, and also we can say that the binary detection is easier. Also, we compare the performance with the other baseline. Our model provide almost better performance with the less inference time and the model size than its counterparts. And also, the results showed that the proposed model can be also robust against removing or noisy input features. And also, you can see the comparison regarding the speed. As I said during my presentation, the proposed model can provide such a trade-off between the efficiency in terms of the accuracy with also the training time and also the model size. Okay, thank you so much for your attention. If you have any question, I would be happy to answer you.
Okay, thank you very much for your presentation. I don't see any question in the chat. Can you say something more about these trade-offs in terms of performance between the tiny model and the complete model? So,
as I said, the main idea is that almost many of the traffic samples are easy for classification. So we can use a tiny or a less expensive model in order to the classification. Just when the tiny model, I mean, is not sure about the input, I mean, about the classification, then we can pass the model to the heavy one. Using this way, we can decline the amount of the computation, memory, and also inference time that we use. Because if we pass all the input data to the heavy model, okay, we can provide a better accuracy, but at the same time, you have to spend a lot of time, computation, memory. So just we pass the input data to the heavy model when it's needed. So we can decline the computation and totally the cost in this case.
Okay, thank you very much.
Thank you.
We go to the next presentation.
Can I stop the sharing?
Yes, thank you.
Okay, thank you so much.
Thank you. Unified multitasking learning versus decoupled transformer-based perception. A comparative analysis. Javier.
Yeah, I'm over here. Okay, so let me share. All right.
Javier, are you there? You speaking?
Mm-hmm.
Okay, we couldn't hear you.
Oh, sorry. Let me.
So let's start again.
Yeah, sorry. Hello, everyone. Today I am presenting our work titled Unified Multitask Learning, Decoupled versus Decoupled Transformer-Based Perception, a comparative analysis. In this paper, we address a persistent architectural dilemma in autonomous driven perception, whether to employ unified multitask learning frameworks that share computation across tasks, or modular multimodal pipelines that prioritize task-specific accuracy. Our goal is to provide a systematic empirical comparison of these two paradigms using identical experimental conditions. Environmental perception is a cornerstone of advanced driver assistance systems and autonomous vehicles. A vehicle must interpret complex roads scenes in real time. This involves multiple correlated computer vision tasks, particularly object detection, responsible for identifying dynamic agents, such as vehicles and pedestrians, and semantic segmentation, which delineates structural components such as drivable areas and lane markings. Historically, these tasks have been solved using CNN-based architectures, specifically one-stage detectors, such as the YOLO family. However, recent advances in vision transformers, particularly DETR-based models, have introduced end-to-end detection frameworks capable of capturing long-range contextual dependencies. At the same time, multitask learning approaches aim to unify detection and segmentation under a shared backbone to maximize efficiency. Despite the adoption of both paradigms, there is still limited systematic comparison between them in autonomous perception settings. This gap motivates our study. In this work, we compare two perception strategies. First, the multitask learning approach represented by YOLO-PX. YOLO-PX is an anchor-free architecture derived from YOLO-P. It uses a shared CSP darknet-based encoder and 3 task-specific decoders, an object detection head, a drivable area segmentation head, and a lane segmentation head. Its main advantage is feature reuse. The backbone is executed once and shared across tasks, reducing redundant computation. However, as discussed in the paper, MTL models may experience optimization conflicts between heterogeneous tasks, a phenomenon known as negative transfer. In contrast, we propose a decoupled multimodal system. This architecture separates object detection and drivable area segmentation into 2 specialist streams. For object detection, we use RTD-TRV2, a real-time detection transformer optimized for efficient deployment. Unlike CNN-based detectors, RTD-TRV2 follows a fully end-to-end paradigm without non-maximum suppression. It incorporates an efficient hybrid encoder combining intra-scale interaction blocks and cross-scale fusion, and an uncertainly minimum query selection mechanism. These components reduce the computational overhead while preserving the global context modeling capabilities of transformers. For segmentation, we adopt YOLO 11 nano segmentation, which is an instance framework based on prototype masks and mask coefficients, enabling efficient real-time segmentation. Importantly, in our comparison, we focus only on vehicle detection and drivable area segmentation, since these are sufficient for high-level planning in many autonomous driving scenarios. To ensure a fair comparison, both paradigms were evaluated using the BDD 100K benchmark dataset. BDD 100K contains 100,000 driving videos with annotations for multiple perception tasks under diverse weather conditions, times of day, and road environments. We use the Fisher split for detection with the original classes. Both models were fine-tuned using PyTorch on a workstation equipped with the specs you can see here. And importantly, for the decoupled system, inference latency was measured sequentially, summing the execution times of both models, simulating a worst-case single GPU scenario. We evaluated MAP50 and MAP5095 for object detection, MIOU and pixel accuracy for segmentation, and FPS and latency in milliseconds for efficiency. The most significant results of our study appears in the detection performance. According to the table 2 in our paper, YOLO PX achieves an MAP50 of 93.5 and MEP from 50 to 95 of 56.6. And on the other hand, RTDTR achieves an MP50 of 96.5 and MEP 5095 of 79.1. While the improvement at the MEP50 is approximately 3 percentage points, the gain in the strict-term MEP 59 to 95 metric is a total of 22.5. This is particularly important because MEP 50 to 95 evaluates localization precision across increasingly strict IOU thresholds. The results suggest that the transformer-based detection provides substantially more precise bounding boxes. As discussed in the paper, this is especially relevant under challenging conditions such as partial occlusions, scale variations, and lateral traffic scenes. From a safety-critical perspective, higher localization fidelity directly impacts distance estimation, collision risk assessment, trajectory planning, and therefore the decoupled architecture significantly enhances detection robustness. For drivable area segmentation, YOLO PX achieves an MIOU of 93.1%, an accuracy of 97.9%, and YOLO achieves a total of MIOU of 91% and an accuracy of 97.2%. The difference in MIOU is 2.1 percentage points. As discussed in the paper, this represents a modest degradation when moving from a shared MTL backbone to a lightweight non-segmentation model. However, both models deliver sufficiently accurate drivable area estimates for downstream planning and control. Qualitative inspection indicates that most segmentation errors occur in thin or ambiguous border regions. Here in the efficiency analysis, we can see that yellow PX achieves a total of 15.95 milliseconds per frame, and here we talk about the segmentation results. For durable segmentation, yellow PX maintains a slight advantage, achieving a mean IOU of 93.1% compared to 91% of yellow. However, the difference is relatively small, only about 2 percentage points. In practice, both models provide robust and reliable drivable area estimation, suitable for downstream planning tasks.
Javier, you've got 2 minutes left.
This indicates that the lightweight segmentation model remains operationally effective despite its reduced complexity. Regarding efficiency, YOLO-BX achieves higher throughput at approximately 62.7 frames per second. The decoupled system runs at 43.8 frames per second. Although slower, it still operates comfortably above the commonly accepted real-time threshold of 30 FPS. This demonstrates an important trade-off. We sacrifice some speed in exchange for a substantial gain in detection precision. To conclude, the decoupled architecture significantly improves object detection quality, particularly in strict localization metrics. It maintains competitive segmentation performance while remaining suitable for real-time deployment. Overall, our results suggest that modularity provides a better balance between precision and efficiency than monolithic multitask learning models, especially in safety-critical autonomous driving scenarios. Future work will extend the comparison to additional perception tasks and embedded automotive hardware. Thank you so much for your attention.
Okay, thank you very much for your presentation. I don't see any question in the chat. In your opinion, what are the architectural factors, for instance, the attention mechanism that influence the most this difference between the two models, the unified and the coupled performance, the performance of the two models? Somebody, can you re-enable my mic? Javier needs the microphone.
Okay, perfect. Sorry, can you repeat the question?
I mean, in your opinion, what are the architectural factors such as the attention mechanism that mostly influence the performance of the two?
Well, that may be due to the due to the nature of the transformers versus the more ordinary convolutional networks, mainly because the vision transformers spread the attention evenly across the whole picture, the whole frame. Meanwhile, the CNN neural networks have to disperse that attention in other ways. I mean, that difference in the architecture is mainly what we were thinking about when we were working on this paper, so that we could see how we could measure that efficiency difference. And I think we got some results, seeing that the vision transformers are quite more faster.
Okay, thank you very much. Good. I think we can. We have finished 5 minutes ahead, but I think we can go on with The fourth presentation, multi-access edge architectures for urban mobility, an experimental comparison, Enrico Rossini.
Okay, hi everyone. Can you hear me?
Yes.
Okay, nice. Okay. I will share my presentation. Presentation. Okay, can you see the presentation?
Yes.
Okay, nice. Hi everyone. I'm Enrico Rossini from the University of Modena Reggio Emilia and Italy. Today I will present our paper, Multi-Access Edge Architecture for Urban Mobility, an experimental comparison. See the picture and tell me, think about what's maybe the problem of our cities. You can think that maybe the problem is the traffic, but it's not. Also, it could be, but for the presentation, for this kind of presentation, the problem is vulnerable road users. Cities aren't meant for vulnerable road users. And according to the World Health Organization, there were about 1.2 million road traffic deaths in 2023, with more than half being vulnerable road users, VRU, such as pedestrians, cyclists, and so on. So you can think about maybe the newer cars are safer, right? So because they are fully equipped with sensors and cameras and algorithms and so on, but they have a limited context. But what about current research? So V2X, so vehicle to vehicle and vehicle to infrastructure communication, it's very interesting concept, but it relies on an inexistent and short-range infrastructure. So our approach is based on 5G communication plus MEC. So 5G networks ensures low latency, high bandwidth, high coverage, and supports dense area. And MEC stands for multi-access edge computing, and basically is the MEC server is basically the computational part is ideally located underneath the base station, so the radio access network. So from the moment that a packet reaches the radio station, maybe there's almost zero latency to reach the MEC server. Okay, so with that approach, packets don't flow through the internet, resulting in lower and stable latency as well as higher security. And also we allow services provider to enable new application scenarios in the future. So summarizing, without the MEC, packets needs to reach the BTS and then the mobile core network and reach the cloud server. Then go back to the whole route, passing through potential congestion and the capacity constraint in the mobile core network, for example. But with MEC, we don't need to reach packets, doesn't need to reach the cloud, okay? So resulting in lower latency, basically. Okay, our testbed is the MESA area. MASA stands for Modern Automotive Smart Area. It's basically a living lab located near the city center of Modena in Italy. And it's a typical mixed residential zone frequented daily by thousands of people and equipped with all the infrastructure for testing connected vehicles and autonomous driving, as well as various type of cameras connected, so on. For example, in the picture in the right, we can see the current state of the smart cameras in the area. So, what's the application? The main goal of our application is to notify a user about possible collision with other road users, so vulnerable road users. Okay, to make this one, we need to have a lot of data, a lot of locations directly extracted from cameras in the area and also from GPS-enabled devices such as connected vehicles, as well as our mobile application. Okay. And once the application predicts a possible collision, it sends an alert to the user. Okay, so the infrastructure is made up of two main areas. So the MEC area is composed by the MQTT broker, our main communication hub and protocol, of course, and the VRU, vulnerable user algorithm, that can identify, of course, potential collision and generates the alerts. We also have the MaaS area, where we have CCTV cameras, are basically municipality cameras, where the video feed is processed by the video processing node, and also smart cameras, where the video feed is processed directly inside the camera. Okay, so and then the metadata is published to the MQTT broker via 5G or directly via Ethernet. In the MaaS area, we also, of course, have the video processing node that analyzes the video feeds and publishes the anonymized metadata. But also another instance of the MQTT broker that is bridged to the one in the MEC area to allow for, in the future, device migration between different MEC areas. This one is a video demo that we conducted. The Tesla is our car. You can see the Tesla Vision service in the top part, and in the bottom, our application that alerts the driver for a vulnerable road user, a pedestrian ahead. Okay. I hope the video is smooth enough. Okay, so in this example, the Tesla Vision can't see the pedestrian, but our system can. Okay, our system tells also what type of vulnerable road user is detected. For example, pedestrian ahead, pedestrian from the left, so on. Okay, and in that example, we also have, you can see pedestrians ahead because multiple pedestrians are detected, of course. Okay, that one is the last one. Okay. Nice. This one is another HMI interface, human to machine interface, made up of a LED strip. Okay, I think we can go ahead. Okay, Apart from the interface, we also have conducted some experiments, end-to-end delay. So we tested the latency between sending location packets and receiving response messages with alerts. And as expected, Mac implementation consistently provides lower average latency. Okay, you can see from the
Enrico,
graph.
you've got 2 minutes left.
Yeah, no
Okay.
problem. Okay, so result. The application showcases a solution that is capable of potentially reaching a wide number of users, does not require additional hardware, and is cost-effective in various and deployable in various environments. This work contributes to the objectives of the NOUS project in various ways. And we have additional edge-native applications such as traffic flow estimation with patterns and congestion level, smart parking to predict parking availability, incident and anomaly detection to detect unusual crowd gatherings or dangerous behavior. And we can federate multiple cities through data space connectors. This allows for seamless device migration between municipal areas and service migration across multiple MAC zones. Future works are measure the full end-to-end latency from the moment of hazardous situation is detected to the delivery of alerts, and explore the scalability of the system. Okay, I've finished.
Okay, thank you very much for your presentation. And I check if there are questions. No questions from the chat. So how do this gain in reduction in latency concretely translate into collision risk prediction intervals? So,
okay. Of course, the problem of reducing the latency in the network is to have more time for cameras and the computational part to do their job, so we can ensure with the lowest possible network latency to provide a smooth experience of our system, and then reduce the total amount of latency, of course, from the moment that an hazardous situation is detected from cameras to the send of an alert. Theoretically, this kind of application must have a total latency below 100 milliseconds. So having those kind of latency with the Mac server is very good because we can have more headroom for the rest of the computation.
okay, thank you very much. There is another question in the chat. What criteria you use to consider a road user as a vulnerable road user?
Okay, so basically for us, a vulnerable road user is a pedestrian or cyclist. So and the object detection is computed with YOLO. So YOLO tells us, okay, there's an object in this image, and with a specific algorithm we can locate in the space, so latitude and longitude to that object, okay, detected from the camera. And then, of course, YOLO tells us it's a pedestrian or cyclist, and we can compute the algorithm.
Okay, good. Thank you very much. Is Carolina, are we going to share the presentation, or we should share with the interested people one by one?
Hi. I don't know how we can share the presentation over here. So maybe Enrico, you can share it with me via email, and I can send it to Carlo Alberto.
Sorry, just one thing. So the session is being recorded, and the recording will be uploaded into YouTube. So anyone can then check the recording and all the presentations there. I think there is no need to share the actual presentation, since the recording will be shared among all attendees.
Okay, like maybe in this case, because they are in the same pilot living lab, so this is an exception, like something internal, so we can solve it like this. Thank you. But in general, we have the video.
Selene, you're muted right now.
I have muted. Thank you. Good. So we go to the next presentation, which is DRL-based service allocation for vehicular mobile edge computing. Gasmi, sorry for the pronunciation.
Hello, good afternoon.
Hello.
I'm Kauthar Gesmi, researcher from University of Pisa, Italy. And today I'm going to present our work. Let me share the presentation. Yeah. So today I'm going to present our work titled Deep Reinforcement Learning Based Service Allocation for Vehicular Mobile Edge Computing. So this presentation is organized as follows. First, I will introduce the context and the problem statement. After that, I will present our proposed DRL-based allocation framework. Then I'm going to present the experimental evaluation results. And finally, I will conclude by highlighting the future direction work. So the rapid growth of connected vehicle and intelligent transportation system has led to the emergence of many latency-sensitive applications, such as real-time object detection, collision avoidance, and traffic monitoring. Those applications require fast processing of large volumes of data and guaranteed end-to-end latency. Sending such data to cloud often introduce high and unpredictable latency, which make it unsuitable for time-critical vehicular application. So to overcome this issue, the vehicular mobile edge computing bring computational resource and storage at the proximity of network. Here is the vehicle by deploying edge server near the road infrastructure. So despite its advantages here, when we decide to schedule and allocate such critical service in the vehicle edge computing, we still face many challenges. And this is mainly due to the dynamic vehicular mobility, the variable network conditions, and the strict quality of service requirement of this kind of application. Also, most of the edge service have limited resources such as CPU, memory, and other shared resources. So the goal of our work is to design an adaptive allocation mechanism that maximize the number of the service requests that successfully executed while respecting a given latency or deadline. So our approach is to use a deep reinforcement learning, which allow the system to learn optimal decision through interaction with the environment. And in our approach, we propose like an learning agent at each edge server that decide how many service requests should be executed at each time slot. So our framework is designed here to optimize the service allocation decisions at the edge server by learning from the interactions with the dynamic vehicle environment. Here, mainly to maximize the number of service requests within the required deadline, while the varying of the changing conditions of the environment. Here, at each time slot, the agent observe the current state from the environment. The state here capture two main components here. First, capture the resource availability at each edge server, such as the availability of RAM, the GPU utilization percentage, how many cores are available. Also, capture the service demand, which means how many service requested received at the queue of the edge server. After that, the agent choose the best action. Here we have two actions. The first action is to offload a task to the edge server or to drop the given task. Here, the offloaded task must not exceed the capacity of the edge server, and also should be executed within the given latency. After that, the environment provides a reward. Here, the rewards with objective to maximize the executed request within the latency. So here we have like the main constraint. The deadline should be respected when during the action of the DRL agent. The latency model it's composed of two components. It's the service execution latency plus the network latency, which refer to the communication delay between the vehicle and the edge server. So a request is considered successfully only if the total latency below a predefined threshold. For our experiment, we have used the three data sets. The first one, for our vehicle network, we used GPS trajectory from collected in Roma, Italy. It's taxi trajectories. And to model the network latency, we used Planet Lab, which is like a set of records of real round-trip time measurements. And for the availability resource to model at the edge server, we use a profiling dataset, which records the execution time of heterogeneous service under different resource and workload configuration. So for the result regarding the satisfaction ratio, so here it's remain very high, around 92 and 93%.
You've got 2 minutes left.
Okay. So for the satisfaction ratio remains very high. It's around 92 and 93%, even as the number of the user increase. And this means that the system successfully serves most requests within the latency. Regarding the service utilization, remain well below the saturation, even at high low. For example, here at the 500 vehicles, still under the saturation. Also, we have the schedule latency. Here, the schedule latency is very low, between 7 and 12 milliseconds. And even as the number of users increase, the overhead remain small and bounded. For our future direction, so we plan to extend our framework by integrate multi-edge coordination and multi-objective reinforcement learning. Also to apply privacy in order to secure the mobile clients. Thank you.
Okay, thank you very much. I don't see any question in the chat. So when you have dynamic mobility, how this algorithm framework maintain a high ratio of service and acceptance level? So when this in case of real-time data.
Mm-hmm. Here, when we have like a high mobility, we model the latency from the dataset. Planet Lab test bands. It's like we can measure the network latency dynamically. For example, to extract the current position of the vehicle and to measure the real latency between the current position and the edge server.
Okay, and it keeps also these thresholds in terms of latency, and it can keep the trade-off with service level and also latency. Yeah?
I couldn't hear your questions. Sorry.
No, I mean that in this way, also in real time, then the algorithm.
Yes. Yes, because here we can extract the current position of the vehicle, not like a static latency.
Okay, but also when there is a tiny budget for latency. Yeah?
For our experiment, we used 30 milliseconds as a threshold.
Okay. And it also can be kept also during when there is dynamic mobility.
Sorry?
And this can also be kept, this threshold, when there is a dynamic mobility.
Yes. So here we experienced three deadlines, 30, 10, and the 20 milliseconds. And here the agent is work well with the 30 millisecond. It seems more realistic deadline.
Okay. Good. Thank you very much.
Okay, thank you.
We go to the second last presentation, which is a small LLM useful for cybersecurity. Federico Munoz. I don't know if I pronounce it well, the name.
Yes. Moment. Okay. Well, hello everyone. Is a small LLM useful for cybersecurity? Well, that question not is rhetorical. We generally ask it. We run the different experiments to answer it. And in the next minutes, okay, I will tell you what we found. Okay, the short answer is yes, but with important caveats that I think are just as valuable as the result itself. Okay, first, let me quickly walk you through the structure of today's talk, okay? First, we will start with the motivation, why we care about this problem and why existing solutions are not enough. Then I will state our 4 research questions. After that, I will describe our methodology, the model we choose, the data set we build, and how we applied a lot of fine-tuning. And then, of course, present the experimental result, including a breakdown by vulnerability class and a look at the computational efficiency. And last one, of course, conclusions and future work. Okay, motivation. Let's set the scene. Imagine web applications, I don't know, autonomous car, a lot of digital infrastructure, you know, is the cost of today. And well, they process sensitive data, handle financial transactions, dedicate users, and they are under constant attacks. Okay, in 2024 alone, more than 40,000 common vulnerabilities and exposure were previously reported. Okay, a lot of bugs, to be honest. Okay, 2 of the most persistent categories are cross-site scripting, now as XSS, okay, and SQL injection, both in the OWASP top 10 year after year. OWASP is a kind of classification of this kind of vulnerabilities. XSS allows attackers to inject malicious scripts into different scripts, and other users execute this script. Okay, imagine risking session hijacking and data left, all the things that you like. Okay, and then SQL injection allows attackers, for example, to manipulate database queries, potential ASP tracking, or corruption entering database. Okay. The industry current toolbox has real gaps. Traditional static application security testing tools, okay, SAPs, really on handcrafted expert rules. They struggle to scale, they produce high false positive rates, and they miss subtle or novel patterns that don't match their signatures. On the other side, larger language models have demonstrated impressive code understanding. But a model like, I don't know, Llama 65 billion requires more than 718 gigabytes of GPU memory for inference. Imagine, it's a lot, you know. That is not something that you run in normal CUI and CD pipeline or in your desktop if you like it. Okay, well, in this case, we need something lightweight enough to deploy locally, fast enough to real-time pipeline integrations, and accurate enough to be generally useful, without cloud dependencies and without prohibited hardware. For that, or to be precise about what investigating, we define 4 explicit research questions. First, can a small LLMs fine-tuned with LoRa or outperform SATs tools and zero-shot baselines for web vulnerability detection, another vulnerability detection, and the resources constraints suitable for CUI/CD integration? Second, how does a fine-tuned small LLM compare against traditional SATs and large LLMs without fine-tuning, especially in terms of precision, recall, and false positive rates? Third, what are the computational trade-offs, inference time, and memory footprint between our small fine-tuned model and large alternatives? And last one, can a single multitask model effectively detect both, in this case, XSS and SQL injection simultaneously, or does tax inference limit performance? Okay, well, these questions drive everything that follows: the design of our dataset, the choice of model, and the evaluation protocol. Okay. Our pipeline has 4 stages. First, dataset preparation. This is so important. Maybe it's the most important, okay? But well, we curate 800 real-world vulnerability examples from CV fixes. It's a dataset of automated vulnerability fix pairs extracted from open source repositories, okay? There are a lot of, well, not a lot of, but there are another dataset similar to CV fixes. Second, model selection. We choose code T5 small. It's a 220 million parameters encoder model. Okay, it's smaller than the current models. Okay, and well, in this case, it's especially pre-trained on code understanding and generation task. Okay. Third, we use LoRa fine-tuning, okay, on our accurate dataset and with this code T5, okay. And last one, the baseline comparison. We evaluate our fine-tuned model against 2 baselines: CERN-grep, widely used SAT tool, okay, and zero-shot version of code T5 small. And the detection task is framed as multi-class classification with 3 classes, okay? Safe, XSS, okay, and SQL injection. This is important rather than training separate binary classifiers and train single model to distinguish all 3 simultaneously. Okay, dataset. Let me give you more detail on the data. Okay, because
Federico,
yes,
just got 2 minutes left.
Okay, thank you. Oof. Well, I try. Well, the most important is the data set. Okay, we started from CV pieces released in 2024, which contain a lot of data, a lot of codes, and snippets with this code, no, XSS, EQL, and so on. Okay, we applied a certified split for this data set. We get it 80% for validation and then 10% for testing, and selected only like I said before, 200 for XSS, 200 for SQL, and 400 for Safe. Okay. We use LoRa to pre-train our model. Sorry, because now I pass all the slides so fast, but well. And the result. Okay, result. Let's look at the numbers. Okay, on the 80 sample test set, here's how the three approach compare. Okay, first, again, same grade, then Code T5 zero shot, and our Code T5 LoRa model. Okay, to be transparent, what does these numbers that you can watch in this slide? Okay, F1 score is not high by absolute standard, but this is a preliminary study, to be honest, and we think maybe to increase with another model or with more data. Okay, but in this case, the most important metric here is precision. Okay, our model produced the fewest false positive on any evaluate approach. In a security trial contest, false positives are expensive. Imagine every false alarms require human investigation. Okay, and the result per class, because I only have, I think, 1 minute more.
Yes.
Okay. Yes. Thank you. Thank you. Okay. Well, first, the model has a bias toward predict safe, because the most the most tax safe or the tax safe is the most important in the data set. Okay, then there is a very little confusion between XSS and SQL. Okay, but detect the vulnerability. Okay, and in compositional efficiency. Okay, for model size, of course, Code T5 is smaller than our LoRa fine-tuned version, but the difference is so close. Okay, difference time per snippet with our approximation is the best. It's around 100 milliseconds. Okay. And then I think the not is the most important, but well, the use of GPU memory, like you read, is it's okay to deploy this kind of solution in a edge system or something like that. Well, this is the same limitations. Okay, small data set, only 2 CVC categories, and we need, of course, to check with another data sets, another CVEs, and of course another models. Okay, well, questions? Sorry, thank you.
Okay, thank you very much. I don't see any question in the chat. So In your opinion, what are the characteristics of vulnerability patterns that allow your proposed model to perform, to generalize better than the other two, the SART and the zero sort of inference?
Well, in this case, I think the difference between zero shot and use fine-tune model, I think the most important is that you can adjust new CVs, new vulnerabilities. You can aggregate this kind of codes, this kind of snippets in your fine tune, and your model can learn this problem, because when you use a only pertain model, you can't add this kind of vulnerabilities.
Okay, thank you very much. We can go then to the last presentation of this session, which is smart VRU fed edge pedestrian detection with human in the loop. Jesus Martin.
Hello.
Hello.
Okay, could you hear me?
Yes.
Okay. I'm going to share the presentation.
You can see.
Okay. Could you see the slides?
Yes.
Okay. Okay. First of all, good evening, everyone. I'm Jesus, and today I'm presenting a smart VRU fed, a system we designed to improve pedestrian detection in autonomous cars without ever compromising user privacy. The idea is simple. Cars see a lot of useful data, but sending that data to the cloud is expensive, slow, and raises privacy issues. So instead, we train the model directly on the devices, in the cars, using federated learning, and we add a human in the loop step to correct mistakes and keep the model stable. This combination gives us strong performance while keeping our data private. Here's the plan. I will start with the motivation and related work, then dive into the architecture, the model we propose, and the workflow. After that, I will describe the dataset and scenarios we tested, followed by our results and the future challenge we face. Pedestrian detection is essential for safety systems in modern vehicles, but real-world conditions like bad lighting, rain, or crowded streets make the task difficult. Traditional training requires collecting and labeling huge amounts of data, which is expensive and often impossible because of privacy concerns. Federated learning helps because each device trains locally, but it struggles when the data is very different from one device to another, or when some devices don't have labels. Is the non-IIDD data problem. We propose a three-pillar solution: federated learning to keep data local, pseudo labels to handle and label data, and a human-in-the-loop tool to ensure the model stays on the right track. Together, this makes the system more stable and more accurate. Previous work shows that federated learning can approach the performance of centralized systems without sharing data. But there are two big issues that remain. First, data heterogeneity. The data each car sees is very different, which hinders training. For example, in Salamanca, the car sees narrow streets, and for example, in Berlin, there see a wide avenues, for example. And the second issue is the lack of human oversight. Most systems rely only on automatic updates with no human correction. Other works highlight the importance of trustworthy annotation for retraining detectors. Yet, current federated learning pipelines are passive. They aggregate updates but do not incorporate human feedback. Our work fills this gap by integrating a human-in-the-loop mechanism into the federated training loop, enabling rapid correction of model errors and improved adaptation to distribution shifts. Our architecture is straightforward. A central server coordinates the training, and each client device trains a YOLO-based model locally. We have two types of clients, one with all data labeled and one with unlabeled data that must rely pseudo-labels generated by the global model. All data stays on the device. Only model updates are shared. That keeps the privacy. This is our lightweight annotation interface. It allows users to fix bounding boxes using polygon-based annotations. This is especially helpful in difficult scenes. For example, when pedestrians are partially hiding or the lighting is poor. These corrections help the model learn faster and avoid drifting when the pseudo-labels are not perfect. The workflow is simple. The server sends the global model to all clients. Each client trains locally, either with real labels or pseudo-labels, and if needed, the human corrects mistakes. Then clients send back only the update model parameters. The server averages everything and sends a new global model. And this cycle allows for rapid personalization while maintaining total privacy. We validate this using almost 2,000 urban images. We compare 4 scenarios. Scenario 1 is our centralized baseline, when all the data are labeled and are kept in the same place. Scenarios 2 and 3 test different labeled and unlabeled splits over 15 rounds, and scenario 4 is an extended 40 round to analyze long-term effects and potential noise accumulation. This is an important problem that we talk after. This setup lets us compare how much performance we lose when we add privacy constraints and unlabeled data. The results are compelling. The centralized model performed best as expected with an MAP50 of 0.65. Our federated model achieved between 90-95% of that performance, which is a very good result considering that some clients have no labels and no data is shared. This is the problem of noise we talked before. The human-in-the-loop corrections help stabilize the early rounds and reduce the noise from pseudo-labels. This is a common problem in this kind of problems case. Is the data shift. Precision stays high, meaning the model rarely detects pedestrians where there are no one. Recall is lower, meaning it sometimes misses pedestrians. This is the primary challenge for future work. Overall, smart VRU Fed shows that we can train a good pedestrian detector without sharing any raw images. The system handles unlabeled data well and adapts to different environments. The main challenge is managing cumulative noise in long-term training. In the future, we want to explore personalization, better human-in-the-loop strategies, and real-world deployment on vehicles. In summary, smart VRU feed keeps data private, involves the user, and maintains 55% of the performance of traditional systems. This is how we will trust in the next generation of European cloud and edge infrastructure. And that's all from my side. Thanks for you for listening, and I look forward to hearing your questions.
Yeah, thank you very much for your presentation. I don't see any questions, any question in the chat. Can you please elaborate a little bit better the contribution of this human-in-the-loop labeling in terms of performance reached by the centralized models compared to the federated?
Most of the state-of-the-art reviews don't incorporate human interaction to correct the automatic prediction that models do, and our proposal is to incorporate in this process of detect pedestrians, incorporate a human verification correcting the prediction of the model.
Okay, and how better is doing compared to the centralized learning?
Compared with the centralized model is worse, because when you distribute the learning, metrics become worse, but is the objective is to achieve
Similar performance.
is to lose the less the less performance, maintain the privacy of data.
Okay. Thank you very much.
Okay, thank you very much. Thank you very much to all presenters in this session. Thank you, Selini, for chairing the session. Now we will have a short break, and we come back at 4 p.m. So we see in more or less 20 minutes. Thank you all.
Thank you.
Bye.
Okay, thank you. Okay. So how are you? I understand you can hear me well.
Yes, perfect, Ricardo.
Okay,
Yeah. Just a few minutes. We start at 2 o'clock, okay?
Okay. Yeah. Do you know, please, if the speakers of the different papers, the different presenters, can send me through chat their names in order to present themselves, or to present them, sorry, in order to present who is going to present each session, each paper.
Yeah, they are already here.
Okay.
And they can talk with you.
Okay, yeah, please.
About
send me a private email in order to know who is going to present each paper. I will be very grateful so that I can present you, okay?
Carolina is the first author of each paper that will present the paper?
Nope, but I already sent Ricardo.
Yeah, not necessarily. I understand that no matter who is the author order, maybe it's a different presenter for each paper. So you can send me a private email.
Yeah, I've sent.
Sorry, not private email. Sorry, a private chat. Okay, a private message. For example, for the first paper, decentralizing the future, value creation in data spaces. I think Celia is here.
Yes.
But I don't know if Celia is going to present the paper. So I can ask you.
Yeah. She's going to one. The next one will present it by Diego Valdolmillos. The next again will be Celia. The next one, Carolina, Marco, Luis Cabello, and Fabiano.
Yeah. Okay, so send me to the chat, please, because my memory is very bad. So
you've got it by Slack.
I know Celia, Diego, and Celia are the three first.
I've sent you an.
Okay, thank you, Carolina, because I'm going to make a test for sure if not.
I've sent you
in Slack.
in Slack.
Okay. Thank you so much. Thank you so much, Karina.
Oh.
Okay, maybe as we are a minute to time, maybe Celia, can you please check if you have presenter permissions and so on, so that if you can test your presentation?
Yes, of course. I will try
Okay,
to share. Thank you.
Great.
Okay, I think we can start if Celia is ready.
Wait, it seems I have something to enable to be allowed to share my presentation.
Let me check. Maybe we need to grant you with permissions, but I cannot. Maybe Karina, can we check the presenter permissions? Because I cannot grant permissions for the participants.
Oh, she just left.
Oh, maybe checking if something's wrong with the RF, but usually in the share button, you have this possibility to do.
Yeah. She was
but I
chair
cannot.
in the previous one, so.
Okay, yeah, but maybe it's in every session. I'm not sure, but I think so. Okay, let's wait for her.
Okay. She's back.
Okay.
Oh, Celia, now you don't have microphone according to Zoom.
Okay, sorry, I have to restart the application. Now it seems okay to share my presentation.
Okay.
Yeah, we are seeing the screen.
I'm presenting. I don't know if I'm in full screen or not.
No, you aren't in full screen. We are seeing.
So let me change my lecture.
Yeah, we're seeing all your desktop.
Is it okay like this?
Try to
maybe
do
maximize the window so that, because if not, we are seeing your desktop also for your privacy.
Oh, okay.
Okay, now it's great.
Okay. Thank you.
Okay, so thank you so much to everybody for connecting to the session. Okay, we're having the last three session, data spaces and governance. We have, a tight schedule, okay, because we have check 7 papers. So the idea is, I know you have two previous sessions, but the idea is to have a short presentation about 10 minutes, okay? Then in the 5 minutes between presentations, we can ask you any question that, of course, the participant assistants have. The floor is yours, Celia. Please, Celia Bolonguer is going from Politecnico di Torino, is going to present Decentralizing the Future, Value Creation in Data Spaces by Celia Bolonguer, Fabio Columbano, and Guido Perboli. Please go on.
Thank you, Ricardo. So yes, so just to add that this presentation is in the context of the NOUS project. So Europe's digital transformation is not simply about scaling infrastructure or deploying more computational resources, but it is about redefining how trust, governance, and value are embedded into digital ecosystems. As we move toward federating European data spaces and next-generation cloud infrastructures, governance can no longer be treated as an external legal layer. It must become a programmable component of the infrastructure itself. In this presentation, I will explain how blockchain, and specifically the European Blockchain Services Infrastructure, named EBSI, can serve as a distributed governance backbone across the cloud edge SPC continuum envisioned in NOUS. Europe currently faces a structural and strategic tension in digital infrastructure development. On one side, Hyperscale cloud providers deliver efficiency, elasticity, and global scalability. Their centralized governance model reduces coordination friction and enable fast deployment of services. On the other side, Europe promotes sovereignty, regulatory compliance, distributed trust, and digital autonomy. Frameworks such as GDPR and eDAIS 2.0 require traceability, accountability, and strong digital identity assurance. This creates a structural paradox. Centralization increases efficiency, decentralization increases sovereignty. The challenge is not choosing one over the other, but it is architecturing a system that balances both. This becomes even more complex in a cloud edge HPC continuum. Edge nodes operate under latency constraints. Cloud systems optimize resources pooled. HPC infrastructure operates under performance critical workloads. Trust and governance must remain coherent across these heterogeneous environments without creating bottlenecks or single point of failure. The European strategy for data envisions common European data space across mobility, security, energy, etc. The ambition is clear. Enable secure cross-border data sharing, preserve sovereignty over strategic data assets, ensure regulatory compliance. However, the infrastructure landscape remains fragmented. Different providers, different compliance models, different governance rules, different identity frameworks. In such an environment, collaboration is technically possible, but institutionally fragile. Key questions emerge. How can data usage be monitored transparently? How can value be fairly distributed among participants? How can we ensure accountability without centralizing authority? These governance tensions motivate our architectural proposal. Our research question is, how can blockchain technologies enable distributed trust, governance, enforcement, and programmable value creation across a federated cloud edge HPC infrastructure such as NOUS? Our contributions are structured along 4 dimensions. First, conceptual. We redefine blockchain as a governance infrastructure rather than cryptocurrency platform. Second, institutional. We position EPSI as a European trust backbone aligned with regulatory frameworks. Third, architectural. We propose an hybrid ledger model separating performance from governance anchoring. And fourth, economics. We articulate how technical, economy, and social value can emerge within federated ecosystems. This multidimensional perspective is essential to move beyond purely technical discussion. So blockchain as distributed governance. Blockchain is often misunderstood as a purely financial technology. In our context, it functions as a distributed governance protocol. Traditional cloud systems rely on institutional trust. Users trust providers based on contract, SLAs, and reputation. Blockchain shifts from institutional trust to protocol-based trust. Transaction becomes immutable, events are time-stamped. Consensus mechanism provides collective validation. Smart contract automatically enforce governance rules. Importantly, in our model, blockchain is not a data processing engine. It's a verification and coordination layer. This distinction allows us to integrate blockchain without sacrificing performance. Why EPSI? Among blockchain infrastructures, EPSI is uniquely aligned with European strategic objectives. It is governed by member states via European Blockchain Partnership. It is public permission. It uses proofs of authority consensus, combining governance accountability with energy efficiency. So EPSI provides verifiable credentials supporting decentralized identity, trusted registry, cross-border notarization services. This alignment transforms blockchain from a technical tool into an institutional trust infrastructure. In the architecture we propose, we distinguish 3 operational layers plus an anchoring mechanism. First, the integration layer that includes front-end interface, back-end services, and middleware components. Applications interact with blockchain services through standardized APIs. Second, the PaaS service layer. This layer manages off-chain storage systems such as IPFS or traditional databases. Operational data remain off-chain to preserve scalability and minimize blockchain load. Smart contracts operate at this level to enforce governance, logic, and policy validation. Third, the infrastructure layer. This includes EPSI nodes and the distributed ledger. This design separates the performance plane, where high-frequency operation occurs, and the trust plane, where integrity proofs and compliance evidence are recorded. Anchoring is asynchronous. It does not interrupt operational workflow. This ensures temper evidence without sacrificing scalability. The hybrid approach therefore balances performance, sovereignty, and auditability.
Celia, you've got
Yes.
2 minutes left.
Okay, I was trying to go fast, but I'm still not. Okay, thank you, Caroline. So the architecture enables value creation across multiple dimensions, technical value, economic value, and social value. Data spaces therefore become a accountable ecosystem where values creation is measurable. Blockchain is often criticized for latency and energy consumption. Our hybrid model addresses these concerns directly. Operational workloads remain local, anchoring is asynchronous, proof of authority consensus significantly reduces energy overhead. Sustainability can be reinforced through carbon-aware workload scheduling and verifiable green certification mechanism anchored on-chain. Thus, sustainability becomes quantifiable rather than declarative. And to conclude, Europe's digital future requires embedded trust directly into infrastructure. Blockchain, and specifically EPSI, can provide a sovereign, interoperable governance backbone across the cloud age HPC continuum. The NOUS EPSI hybrid model demonstrates how European data spaces can evolve into scalable, accountable, and value-generating ecosystem. Thank you very much for your attention, and sorry for the timing.
The timing was great.
Oh, okay, thank you. I cannot hear. I don't know if you're talking.
Yeah, sorry, because
Okay.
I wasn't able to enable the microphone again. So because
We all have the same issue.
sorry, Matt. No, I was talking to Carolina through chat because I cannot re-enable. So I think I need the host permissions. Thank you so much, Celia, for the presentation. It's a very, very interesting work. In this sense, any of the assistants has any question for Celia? Okay, if not, I can ask something. You were talking in the presentation about different dimensions, including the economic dimensions for the model. How do you envision to validate the model in terms of the different economic metrics? I don't know, in real environments. How do you think that this could be done in order to validate this economic dimension of the model?
In fact, this work, so that we did another work. I will present it to presentation after. And this work is more the general one, architecture, and the second one will be about the first iteration for the validation of this model. So you will see in the next presentation the proof of concept, the first proof of concept. It's, let's say, the V1 we now share in NOUS project, and we can, I don't know, maybe we can talk about this in the next presentation if you have still questions after this.
No, I think in your new paper, I will make a different question, because I understand that you are going to answer to all of this in the session. Okay, so thank you so much, Celia, for the work.
Thank you very much.
Very, very interesting.
I will stop the sharing to let the space.
So I think the next one is Diego Valdeolmillos, if I'm not wrong, in order to present policy-driven privacy pipelines for cooperative ITS V2X messages in data spaces by Diego Valdeolmillos, Javier Gonzalo Andrés, Victor Martín Campos, and Ricardo Alonso. So Diego, the floor is yours.
Okay,
we can
thank
see
you,
your
Ricardo.
screen, also can hear you, so wherever you want, please.
Thank you, Ricardo. Well, you present in the paper, so I will say the core idea of this paper is simple, that V2X messages are extremely valuable for operation, analytics, and research. But once you collect the messages and share them beyond the safety broadcast, the domain, you have a really privacy risk. So you can really anonymize this from the edge, but this simply is, for example, extra development, or including send several strings for each system is not very valuable. So we propose using data space, using data apps that are application inside data space. So this is our proposal architecture. So we will see a deployable pattern aligned with the NOUS architecture and compatible with the Eclipse data space. So V2X streams are privacy sensitive the moment they are collected, persisted, or shared beyond the safety broadcast domain. So high rate CAN sequences enable trajectory reconstruction. The other kind of messages is DINM semantics can reveal sensitive situation, and CPN might expose bystanders and vulnerable pedestrians and other road users. Also, at the same time, the idea of the European data space are designated for cross-organizational sharing under usage policies. So here the question that we want to resolve is how do we enable legitimate sharing use without turning route dissemination into re-identification risk or linkability of vehicles or pedestrians. So I will explain a little bit the edge of messages that we test here. There are other messages, but we don't try to research about this. But CAN is periodic status and kinematics for cooperative awareness. The dominant privacy driver is trajectory linkability, because they give repeated position and motion reports that can create track even under these messages are under pseudonymous IDs. The DINM E7 driving hazard alerting with time and location semantics. Here the dominant driver is the semantic inference. The context of a rare event can reveal behavior, presence, or sensitive circumstances. And CPN is cooperative perception, so objects and regions are detected by sensor, and the dominant driver is bystander exposure, so object level perception can describe non-equipped road user, include a vulnerable road user. So we don't treat all the kind of messages as one privacy problem. We can treat each of them as different risk surface requiring different transformations. So for this, we have this triad model that we assume four adversary classes. The first is the honest but curious consumer, that they have legitimate access to outputs, but they try to infer identities, trajectories, or sensitive situations from what they receive. The second are external observers, that they correlate leaked derivatives across time and space and across sources. The third is insider misuse, either or provider size or in the common service in the data space, where privileged access enables correlation through laws or intermediates. And the last one is re-identification, attackers using auxiliary data to retribute pseudonymous trace. So the aim is the preserved utility for high frequency messages like this, and even driving cooperative intelligence transport system use. So while in a way we reduce the privacy risk from persistent collection. So here is the architecture pattern in NOUS terms. At the top we see the data space common service. We also had the NOUS data agents collecting. Is conceptually like an EDC style connector with a control plane and data plane. The control plane handles publishing offers, attaching policies, and negotiating contracts, and the data plane performs the actual transfer under the negotiation terms. So the crucial part is inside the provider that coming, for example, for RSUs or MEC, using normally MQTT, because these kind of messages are from real time. But how can they ingest this data using adapters and provide this anonymization with the data app? So the data app will apply this privacy transformation. So the architecture keeps raw strings inside the provider perimeter. So is the way that we want to do. And we first normalize the string with an ingestion adapter, and then the privacy data app applies the profile-driven transformation to anonymize the data. So for each of these messages, we have a different pipeline. For CAN, the attack we care is about the trajectory reconstruction for repeated beacons. So we will start buffering CAN in short windows, for example, 10 to 30 seconds to bound the maximum track length that can ever expose it. Next, we generalize space by mapping position for deterministic route segments or grid cells. Then we coarsen time and motion. We quantize timestamps to 1 to 5 seconds to discretize the kinematics. And finally, we apply the canonization gate at the cell time level. So the output will be anonymized. For DNN, the risk is the semantic inference. So we first apply event type spatial clocking. We adapt location precision based on event severity. So higher sensitive alerts are published and coarser granularly. Then we smooth time by rounding of bucketing timestamp. Enough to reduce the exact time of inference while keeping the event sequence. Third, we deduplicate and save the rate, limiting repeated sampling. And fourth, we redact selectively. We remove any fields not needed for the purpose. And for CPN, the main ethical is.
You've got 2 minutes left.
Okay. Are regulatory issue and third-party exposure. So the pipeline start with object suppression, then we convert to grid conversion with static cell time occupation grids. After we aggregate density we output counts and density per fair regions, and only if use case truly requires motion, we permit ephemeral tracks. So this is the transformed data. So I will continue with this. For this, we have different privacy profiles, configuration, different for example, for traffic analysis or research safety. So this is our structure. And for validation, we plan 3 things. The first is the governance and feasibility, verify negotiation contrast acceptance, and profile evidence logs. Second is the privacy invariance, that we confirm that no route parallels egresses or servers. And third, the utilitariization, that we measure whether errors versus raw aggregates. So to wrap up, the contribution is they provide a specific message thread and privacy model for this kind of messages for B2X. Second, we compact this in the NOUS aligned architecture. And third, we operational the pipeline as version configuration-driven privacy profiles with some deterministic parameter logging and multi-view producing. And for future work, we want to adaptive policy-driven profile selection using some contextual signal, while keeping selection editables and contract stable, plus some living lab validation in make deployments with MQTT, and use better cryptographic commitments to this kind of profile version and release logs. And that's all. Thank you.
Thank you so much, Diego, for the presentation. Has any of the assistants or the attendants any question for Diego, please?
Yes, I've got one.
Thank you. Go on.
Could this policy-driven approach be extended to other types of real-time streaming data beyond V2X messages?
Yes. We tested this with real messages from data from France, Paris. So also I have another slide to show this. But this kind of pipelines we can easy to use with other kind of data, real-time data or other structured data that is in batches, for example.
Okay, thank you, Diego. Another question maybe for Diego.
Yes.
Okay,
Yes.
please, Gaetano, please.
What was the key design trade-off that you had to make in the approach, like accuracy versus complexity or other type of trade-off?
Can you repeat, please?
If you had to as key design, if you had to do trade-off in your approach, for example, between accuracy and complexity, or other kind of trade-off that you did in your
Well, it depends that what you want to do with the data. This is why we design different profiles. But if you need for some research or some actions in real time, you will need raw data. But this is the core idea of this is that maybe you have this data to share with other companies or also in public. So you cannot do this because it's GDPR protected. So this is why we thought about this kind of system. But if you wanted to research, there will be some trade-offs and something that it will be not. You cannot detect where is a pedestrian or a vehicle in a position because we move this in some coordinates and so on.
Okay, thank you.
Thank you so much, Diego. So next presenter is again Celia Boulanger, presenting blockchain-based data lifecycle in data spaces, by Federica Gentili, Celia Boulanger, and Guido Pervoli. Okay, we are seeing your screen,
yes.
Celia. Yeah, we are seeing all
But
the
I'm
desktop,
not
you know.
full. Yes, I'm not full. Anyway.
That's great.
Thank you, Ricardo.
Thank you. Please, the floor is yours.
Thank you. So the core problem here addressed is not data sharing itself, but governance continuity. In federated ecosystems, data can move across organizational, technical, or jurisdictional boundaries. When this happens, maintaining consistent provenance, policy enforcement, and compliance evidence becomes significantly more complex. This presentation will follow 4 steps. The first step, the governance challenge. Second, the conceptual foundations. Third, the architectural framework and implementation. And fourth, the incremental validation approach. Data spaces represent a decentralized and federated approach to data management. Participants share data under common standards while preserving sovereignty. This federated structure eliminates central control. Each participant retains ownership and policy authority over its data. However, the absence of single controlling entity creates lifecycle discontinuities. Once data leave their original domain, it becomes difficult to ensure that provenance remains traceable, that usage policies remains enforceable, and that deletion of or withdrawal operations are verifiable. This issue is amplified in cross-border and cross-sectors context, where regulatory compliance must be demonstrable across jurisdiction. Traditional lifecycle management models were designed for centralized systems. They assume administrative control over storage, login, and enforcement mechanism. Federated ecosystems require distributed and collectivity verifiable mechanism instead. The data lifecycle typically includes creation or collection, storage and maintenance, usage, update or transformation, and deletion or withdrawal. Each stage introduces governance requirements. During creation, provenance metadata must be recorded accurately. During storage, integrity and access control must be maintained. During usage, policy enforcement and consent constraints must be respected. During updates, version history must remain traceable. During deletion, regulatory requirements such as the right to erasure must be satisfied. In centralized infrastructures, these controls are internally coordinated. in federated environment, lifecycle governance must persist beyond organizational boundaries. Data space provide interoperability and sovereign exchange. They are often structured around connectors and governance frameworks inspired by the International Data Space Reference Architecture. These mechanisms enable participants to negotiate access and attach usage policies. However, they do not inherently provide immutable temper-evident evidence or lifecycle transitions once data circulate among multiple actors. In other words, interoperability does not automatically imply verifiable governance. An additional distributed evidence mechanism is required. Blockchain provides an happen-only ledger replicated across nodes and secured through consensus protocols. This architecture ensures tamper-resistant login of governance-relevant events. Smart contracts allow lifecycle rules to be encoded as deterministic logic. When triggered, they record cryptographic commitments that can be independently verified. However, blockchain is not suitable for high volume or sensitive data storage. Scalability and regulatory constraints require hybrid architectures. Therefore, in this framework, data remains off-chain, while the blockchain stores only conceals evidence such as hashes, identifier, and policy references. The proposed framework integrates blockchain as a complementary trust layer. The central architectural principle is the strict separation between data and evidence. Dataset remains stored and managed by data space connectors. The blockchain layer records lifecycle events commitments. At creation, a dataset hash and provenance metadata are encoded on-chain, establishing verifiable origin. At update, new versions are created rather than replacing previous states. Each version hash is linked to the prior version, ensuring complete change traceability. At withdrawal, deletion is modeled as revocation. A blockchain transaction references the previous dataset hash and records the reason for withdrawal. Through selective anchoring, lifecycle governance becomes auditable without compromising scalability. Blockchain systems face the scalability trilemma. Decentralization, security, and scalability cannot be all maximized simultaneously. Recording high-frequency events or large datasets on-chain would introduce latency and storage overhead. The framework addresses this through selective anchoring. Only governance-relevant commitments are stored on-chain. This preserves integrity and verifiability while maintaining operational efficiencies. The proof of concept relies on a permissioned infrastructure compatible with the European Blockchain Services infrastructure, ensuring performance and regulatory alignment. The conceptual framework is operationalized within the NOUS data space. Three lifecycle operations are implemented: resource addition, resource update, and resource withdrawal. During resource addition, a smart contract records time step, metadata, attributes, authentication-related information, and dataset hash. During update, a new version is created and chained to the previous version via cryptographic hash linkage. During withdrawal, a revoke function records the revocation event and references the preview dataset state. This design ensures that the lifecycle transitions are notarized while raw data remain off-chain. Validation follows technology readiness levels. At TRL4, functional correctness of smart contract is validated in a controlled EVM-compatible environment.
Celia, you've got 2 minutes left.
Sorry, yeah. At TRL5, the system is deployed in a distributed permission configuration using Hyperledger Besu. This stage evaluates interoperability and operational stability. At TRL6, integration occurs in an EPSI-aligned environment, addressing governance, alignment, and institutional trust. This structure progression demonstrates increasing maturity from component validation to ecosystem integration. The communication interface evolved with system maturity. Early stage rely on webhook-based callback for deterministic blockchain triggering. At higher maturity levels, the architecture transition to message-oriented middleware, supporting asynchronous processing and reliable event delivery. This enhances resilience, scalability, and fault tolerance in federated multi-nodes environment. To conclude, blockchain can serve as a distributed evidence layer, supporting verifiable lifecycle governance in federated data spaces. By separating data from evidence and adopting an hybrid on-chain, off-chain architecture, the framework ensures scalability, regulatory compliance, and temper evidence traceability. The proof of concept demonstrates that blockchain can complement data space middleware without replacing interoperability mechanism. This approach contributes to trustworthy and sovereign digital ecosystem, where governance is embedded at the architectural level. I'm done. Thank you.
Thank you so much again, Celia. Again, very, very interesting work. Maybe one of the attendants have any question for Celia? Okay, so thank you so much again, Celia. I have a different question, if it's okay for you, okay? Because I understand that this work will, of course, connected with the previous one. Listening to both of them, what do you think that what could be the more interesting incentives for encouraging different organizations to use a solution like this? How do you think about that? You know, in order to how convince different organizations to why use this solution? What do you think that could be the main focus?
Thank you for the question. So yes, I'm trying to recap everything. But yes, but first, this work and this architecture was thought for NOUS and a European project, and of course we encourage all European to on board on this platform, because there are many plus on this platform, but one of them is the compliance with the GDPR. So maybe it's the most evident. But
I think it's not a easy question, because I'm talking more in the future. Okay, I understand that. But I think it is a good point. Or only to know ideas for the future. Okay, but okay, again, I think the work is very interesting. I think again for both presentations and the answer. Okay, I think it's a very good point. Thinking about the data privacy and this regulation. Thank you so much, Celia.
Thank you.
I don't know if any attendant has an additional question for Celia. Okay, thank you so much again, Italia. Really.
Thank you.
Okay, so next presenter, if I'm not wrong, is Carolina González Cambero. It's okay. She is going to present Triaxial Framework for Digital Resilience Compliance Assessment in Insurance by Carolina González Cambero, Paula Lamo, and Javier Reiner. So Carolina, maybe you need permissions, I don't know. Okay, we can see your screen. Maybe the top of your camera is, okay. Okay, now we can see you. But by the moment, we are not hearing you.
Hello?
Okay, now we can hear you.
Thank you.
Oh, thank you, Carolina.
I'm going to share my screen.
Okay.
And now?
Yeah,
Yes.
it's starting the screen. We can see you are, I think, the entire window of the Acrobat.
Only Acrobat, no?
Yeah, I think so. Yeah, it's a PDF browser.
Okay. 1 second. Okay. Can you see my Acrobat, no?
Yeah. I think it's okay. So the floor is yours whenever you want, please.
Okay. 1 second. Thank you very much for the opportunity to present my work today. My name is Carolina González, and today I will to present a framework entitled a triaxial framework for digital resilience compliance assessment in insurance. Today, I will briefly cover these items. First, the context and motivation, then the methodological gap that we identify. After that, I will present the triaxial framework and the technology implementability index, then the DORA evaluation methodology, and finally, an illustrative case study, results, discussion, and conclusions. Insurers is a highly regulated and trust-dependent sector. At the same time, digital transformation is accelerating rapidly. Technologies such as artificial intelligence, IoT, distributed ledger technologies, and cloud and edge computing are becoming central in insurance process. However, the regulatory environment has also evolved. The Digital Operational Resilience Act, or DORA, introduced a binding ICT obligation across European Union. This means that technological viability is no longer evaluated only in terms of performance, efficiency, or cost. In this image, we can see the core of the problem. Technology readiness levels, or TRLs, measure the technical development stage of a technology. ISO and governance frameworks define control structure and security requirements. Resilience testing guidelines evaluates technical validation and robustness. However, these tools are fragmented. So the question here is how we do unify these criteria into a single decision metric. Currently, there is no integrated decision framework that connects implementability and regulatory alignment. This is the gap that motivates our research. To address this gap, this paper proposed 3 elements. First, a triaxial conceptual framework for structure analysis of digital adoption. Second, a quantitative metric, the Technology Implementability Index, or TII. Third, a systematic method to translate DORA requirements into measures, indicators. And fourth, a visual prioritization model to support strategic decision making. The objective is to provide a structured decision support framework for regulated innovation. To make the assessment the triaxial framework is the conceptual core of this research. We argue that technology adoption in regulated sectors must be analyzed through three independent axes. The first axis is enabling technologies like blockchain, IoT, edge, etc. The second axis is impacted insurance functions such as underwriting, pricing, claims, fraud detection, and operational continuity. And the third axis is implementation barriers, technical, regulatory, organizational, and economic. The key idea is effective transformation only occurs when the three axes are aligned. To make the assessment comparable, I introduced the Technology Implementability Index, or TII. TII combines maturity, applicability, and viability. It is scored from 0 to 3 and normalized for a percentage. Maturity is based on TRLs and developed states. Applicability is the functional fit to insurance process, and viability captures feasibility economic, organizational, and regulatory, including DORA. By default, we use equal weights in this equation, but they can be adjusted in other environments. We translate DORA into measurable indicators with 3 steps: DORA article, operational control requirement, and quantitative indicator. For example, an incident reporting becomes the percentage of incidents reported within the deadline. This creates traceability from regulation to evidence. I apply the approach to a medium-sized European insurer company. In this case, we evaluate 3 technologies: permissioned blockchain for claims, IoT and edge for telematics, and AI for fraud detection. Evaluation criteria, pues, TII score and DORA compliance governance matrix. And so what? What decision does this framework enable? Pues this framework prioritizes investment under DORA, identify remediation needs to deploy, and compare heterogeneous tests with other lens. This is the result of the investigation. IoT and edge have the highest TII. Blockchain is balanced but has integration organizational challenges. AE has the lowest score due to governance and regulatory constraints. So maturity alone does not guarantee adoption. IoT aligns strongly with risk management and resilience. Blockchain performs well in third-party management and information exchange. AI is weaker in governance and traceability. For AI, the real challenge is governance, transparency, and regulatory defensibility. Here we can see the real chart. which it's so performant across the 5 DORA pillars.
Carolina, you've got 2 minutes left.
Okay, thank you. And the traffic lights summarize compliance in a single way. This visual supports prioritization. Discussion. The main findings: regulatory feasibility is decisive. Governance capacity drives deployability, especially for artificial intelligence. TAI enables structured comparison. Limitation, expert judgment or need for more validation. Future work, Delphi panel, sensitive analysis, and addition support tool. And finally, conclusion, this work provides the triaxial framework, the TII, and the method to turn DORA into measurable evidence. Digital resilience is now a prerequisite for innovation, an afterthought. Ensures that master compliance engineering can turn regulation into a competitive advantage. And thank you.
Thank you so much, Carolina, for your presentation. Very interesting. Any of the attendants has any question for Carolina? Okay, so I have one question, Carolina, please.
Okay.
How adaptable or maybe what do you think could be the main challenge in order to adapt your TIA model to other regulated sectors, for example, healthcare or energy? I don't know. Do you think it's possible, and which would be the main challenge for that?
I think it's possible. You only have to select your DORA pillars. In this case, I select the $5 DORA pillars that take part in insurance companies. You can use the same model with other pillars that apply it with this healthcare, financial, or other environment.
It sounds like you've got a solid concept in mind. The big
Okay.
Digo una cosa, perdona. Se me ha puesto
Yeah,
así.
so someone was invited. Okay, so thank you so much, Carolina. Maybe
you.
another attendant or another smartphone has any question for Carolina. Okay, thank you so much again, Carolina.
Thank you.
Then we go with Marco Gagetti. Okay, he is going to present towards trusted and interoperable data sharing, data spaces and blockchain in the MASA project, and EBSI-based architecture by Marco Gagetti, Marco Mamei, and Federica Gentili. Sorry, because my Italian is the worst. So Marco, how are you? Yeah, we can see you. Maybe you are. Maybe Carolina, we need to grant permissions for Marco, okay, so that he can use his microphone. Anyway, I think, yeah, because by the moment you are muted, I don't know, Carolina. I mean, Carolina Villoria in this.
I know. I cannot find Marco Gagetti.
Yeah,
I'm finding
his
Marco
name is
Mamei.
Eleno, okay? Eleno with E, starting E.
Okay.
Yeah. Okay. Thank you so much, Carolina.
Okay, thank you. Good morning, all. And good morning to you. Thank you very much for your chairmanship. Okay, now I will just a moment.
Yeah, no worries.
Do you see my screen?
Yeah, it's loading. We can see your PowerPoint. Oh, indeed, we can see the entire. Okay, now we are seeing right now the speaker notes. You know.
That's one better. Okay, I try to change the screen.
Okay, yeah. We can see the slides. It's okay, but we can see also the notes. Maybe it's not what you want, but it's okay.
Just a moment, I retry it. I retry. Just a moment.
Yeah, no worries.
It's so complicated. the life with these systems.
Yeah, the PowerPoint with the two screens is a mess.
What is this one? Do you see the screen?
It's loading right now. We can see the again the PowerPoint in editing
but I
mode.
will try to. And now?
Okay, it's okay.
It's good.
We can see we can see only the presentation, only the slides, so it's okay.
Okay. Just a word to start. I will describe you the paper that we wrote for the NOUS project. The paper is Toward Trusted and Interoperable Data Sharing, which is something that is studied about the MASA system. MASA system is the Modena Automotive Smart Area, which is a more or less limited area in the Modena city, in which smart car and smart crossing line, smart people, smart biker, and etc. Works all together to allow a sort of combination of clear and safe motions for the future of a smart city. Okay. I will start by introducing the motivation of this paper. Then I will explain the limits of the traditional smart city platforms. After that, I will introduce data spaces and the role of the blockchain and the BSI. Finally, I will show how these concepts are applied in MASA, focusing on special use cases, which is the MaaS use case. What is the problems toward trusted and interoperable data sharings? European cities increasingly rely on digital infrastructure to deliver mobility and public service, but data fragmentation and regulatory constraints still prevent effective integrations. So, of course, this paper argues that trusted data sharing cannot be achieved through centralized platforms, of course. Instead, it requires federated architectures combining data space and public trust infrastructures such as BSI blockchains. MASA demonstrated that identity, consent, accountability can be enforced by design a real city scale. Just a moment. Excuse me. The mouse has been too much freedom. Okay. Slide 4. Excuse me. Okay. The core thesis of the paper. The core thesis of the paper is simple but strong. Trusted and interoperable data sharing requires federated architectures rather than centralized platform. Data space provides governance interoperability, while public blockchain infrastructure provides verifiable trust. MASA showed that this combination work in practice and just not in theory. It's something that more than a simple theory. What is the limit of a traditional smart city platforms? Traditional smart city platforms typically rely on centralized data aggregations. This reduces sovereignty and creates dependency on platform owners. Trust is implicit, rendered verifiable, and compliance is often handled after the fact having happened. This limitation makes such platforms unsuitable for long-term, large-scale, and cross-border urban services. What are federated data spaces in this context? Federated data spaces offer, excuse me, I don't know what the phenomena continues to move the, okay. I return back, okay. Federated data space, each data provider retains control over its data and define assets and usage conditions. Interoperability is achieved through open standards rather than proprietary APIs. Value is created through shared ecosystem, not through extraction of central ownership. Why blockchain is needed? Data space alone are not sufficient if trust cannot be verified. In multi-actor and cross-border scenarios, identity, consent, accountability must be cryptographically provable. Auditability is especially important for public service and the regulatory oversight. Excuse me. Okay. This is the diagram of MASA blockchain oriented. MASA is addresses are key challenges for city today. How to share a urban data in a way that is trusted, interoperable, and governed. The problem here is not to have data availability, but to have trust and coordinations. MASA connect this physical layer to a blockchain-oriented architecture, ensuring data integrity, traceability, controlled access without storing raw data on chain. So MASA is just not a city pilot. It can demonstrate how NOUS enables trusted, sovereign, interoperable data sharing, turning urban data into a reliable asset for digital services. ABSI as infrastructure, as a public trust infrastructure. ABSI is a permissioned blockchain services based on European infrastructures. ABSI is a permissioned blockchain governed by all diffused system into the several big states in Europe. It provides decentralized identifiers, verifiable credentials, and smart contracts. Most important, it is aligned with the two major requirements of a European Commission, GDPR and AIDS, and European public sector requirements. What is the ABSI integration in MASA? In MASA, all actors, users, operators, sensors, and institutions have verifiable digital identities. Consents and access rights are enforced through smart contracts. Events such as booking or service usage are notarized as cryptographic proofs. At the same time, all sensitive data remains off-chain under institutional control. What is the MASA layered architecture? MASA is organized as a layered architecture. It starts from physical infrastructures such as IoT devices and vehicles. Edge and fog computing handles low latency processing and data minimizations. On top of this, data integration, trust, application, and governance layers enable scalable and interoperable services. And now we can introduce quickly the MaaS use case. MaaS as mobility as a service use case, multiple operators, multiple mobility, cooperation without centralizing their data. Users interact through a unified interface and as a service based on verifiable identity infrastructures. Settlement, auditing, and compensation are automated and transparent. Concluding, what are the key contributions of MASA to these systems? MASA operationalizes European digital strategies in a concrete urban context. It combines data sovereignties, interoperability, and the verifiable trust. Compliance is built into the architecture rather than added later. The project provides a reusable blueprint for trusted and interoperable small cities in Europe. Okay, thank you for your attention.
Thank you so much, Marco. So, any of the attendees has any question for Marco? Okay, I have one. Thank you so much for your presentation. Again, Marco, it's a very interesting project for sure. How do you think, do you think it's transferable, the results, your solution, your architecture, maybe to other cities or maybe to other sectors or, I don't know, other planes, other urban planes beyond mobility? I mean, any of them? Or
One
the
answer
cities,
four times. One answer four times. For city, yes, of course, but in European environments is easier because we have similar rules, similar regulations, similar constraints about the GDPR regulations. For instance, in USA, we haven't. It's very difficult to apply the same rules. So it needs some regulation at higher levels to harmonize what we use as strictly related GDPR regulations in Europe. Okay, this is the kernel of the situation. We notarize all the situations, and how can I say, since sensible data are not recorded in the systems. In this case, for instance, in USA or Australia or what else other countries, they have not these constraints. So they maybe would like to record other data that we are not authorized to record. So probably we need different architectural, at least at blockchain level, at least. Secondly, the system could be exported to other environment. Maybe, I'm not so expert in that, but maybe in railway systems. Maybe to organize better crossing of railway systems in very busy cities, mixing underground systems with the surface trains and other kinds of transportation systems like bus or what else. I have more or less the idea that it could be easier to be transformed, of course, with the same constraints of GDPR in a support for transportation system, not directly related to automotive. Okay.
Okay. So thank you so much again, Marco, and congratulations for your project.
Thank you.
Okay, so next colleague is Luis Cabello de los Cobos de Toro. He's going to present Evaluating IoT Protocols, a governance-oriented comparative framework by Luis Cabello de los Cobos de Toro, Paula Lama, and Javier Reiner. So Luis, I don't know.
Hello, can you hear me?
Yeah, we can hear you well, Luis.
Okay.
We can see see
Okay.
you right now. Okay.
Okay. Thank you so much,
Thank you so
Ricardo.
much, Luis.
I will
So probably
insert.
Carolina is right now granted you permissions to share your screen. Please check.
Yeah, you should have permissions.
Okay. Can you check, Luis? You know,
Yeah, I'm trying because I'm not familiarized with Zoom. Sorry.
no worries. It's a green button at the bottom of the
Okay.
window.
I
Okay.
can see. Perfect.
Okay.
Can you see?
Yeah,
It's
it's
loading. Yeah.
working.
Right now we can see your entire PowerPoint.
Okay. Now in big, no?
Yeah. Now it's full screen. So whenever you want, the floor is yours.
Okay. Thank you so much, Ricardo. Thank you so much, Carolina. Distinguished colleagues, it's a pleasure to present our research titled Evaluating Industrial IoT Protocols, a governance-oriented comparative framework. This is a study authored by me, Luis Cabello Los Cobos de Toro, Paula Lamo, and Javier Reiner. This work presented the need for integrating data governance directly into the communication layer of industrial IoT ecosystems to ensure long-term data governance and sustainability. Data governance serves as the framework of policies and standards that ensure the quality, trust, business value of corporate information. While prior academic attention have focused on the application and cloud layers, the foundational role of the communication layer is often overlooked. No, this is a critical gap because protocol level features such as native cryptographic mechanism or messaging semantics directly influence the enforceability of governance policies at a higher architectural level, which is indispensable for resilient AI-driven industrial systems. So the context is basically we have different sensors, different systems with different non-standardized IoT information, and often this information is governed after the ingestion of the messages in the systems, and the main idea of this study is try to focus in the communication layer protocol for try to understand if we can by design enforce this data governance capability. For that, we will take a look of the OSI model. The traditional 7-layer OSI model is often reinterpreted into a more streamlined 3-layer model consisting of the perception layer, that is the responsible for acquiring information from the physical environment through sensors and for interacting with via actuators. The presentation, session, transport, and network layers can be mapped to the transmission layer in the IoT communication protocol. And this transmission layer ensures that the data generated at the perception level is really deliberated to higher layers. In contrast, we have the application layer, that the application layer in the traditional OSI model, of course, maps the application layer in the IoT communication protocols architecture. And this layer manages the data once delivered from the transmission layer, exponsing it and in a structured and meaningful way for monitoring, control, and to make a decision making. Understanding this model is essential for analyzing how the different protocols handle data and each state of the communication lifecycle. For that, this slide categorizes 7 key communications IoT protocols studied for different industrial integration, ranging from high enterprise connectivity to low-level hardware control. For example, MQTT and lightweight end-to-end serves a lightweight bandwidth efficient solution for constrained IoT devices and IoT devices, while OPC UA and AIM-T Connect provide the semantic frameworks necessary for structured data exchange across PLCs, SCADA, and CNC systems. For high-speed safety critical applications like robotics, DDS offers brokerless real-time control, whereas REST APIs facilitate standard web and cloud services integration. Finally, Modbus TCP/IP remains a bridge for incorporating legacy industrial assets into a modern Ethernet-based architecture, ensuring that all the drives and methods can contribute to the planned data ecosystem. So with this landscape, we design a framework aligned with the Dama Book 2. We focus in 3 critical pillars: data security, data architecture, and data operation management. Each of these metrics we define associated with a qualitative scale from 0 to 3, allowing for a structured comparison of the intrinsic governance support within each protocol. The security pillar assess 3 core dimensions: native security, which evaluates whether a protocol provides Boolean cryptographic service for confidentiality, integrity, and authentication, rather than relying on standard layers like VPNs. Data integrity level focuses on the specific cryptographic or no cryptographic mechanism used to ensure that that data has not been altered during the transmission, and entity authentication level that determines the method and extent to which participants in a network are cryptographically authenticated, ranging from unilateral and mutual granulated level. For architecture and operation, we evaluated data and interoperability that measures the ability to define data structure and semantic context to ensure consistent interpretation across different systems. Data structure level to determine the semantic richness and the structure of data models, and additionally, the life cycle management and reliability that assess the native mechanisms such as quality of service that guarantee the data delivery, persistence, and proper sequencing. After apply these metrics, we do a empirical benchmark reveals a significant gaps in governance maturity in communication protocols. OPC, yeah.
You've got 2 minutes left.
Okay. OPC UA and DSS emerged as leaders, scoring 17 and 15 out of 18 respectively. The results highlight a fundamental divergence between information-centric protocols and those designed primarily for data transport. Protocols such as OPC UA and DDSD demonstrate advanced maturity by natively integrating security and semantic interoperability. In conclusion, our study confirms that the maturity of the data governance varies significantly across the industrial IoT landscape, with OPC UA and DDS serving as reference solution for industrial context. We observed a trend towards convergence where future protocols will likely incorporate standardized data models to reduce the need for complementary governance mechanisms and facilitate seamless ecosystem integration. Future work will proceed along two primary trajectories. First, the proposed data governance framework will be extended and validated by applying into a broad range of prominent IoT protocols as CoAP or some other proprietary IoT protocols. And of course, the framework of metrics is going to be extended. So thank you so much for your attention. It's a pleasure for me to do this presentation.
Thank you so much, Luis. Okay, so any question for Luis from our attendant? Okay, I have a question, Luis. Again, thank you so much for your presentation on your work. Did you plan, maybe not in the short time, probably I understand, because I understand that your work is within a doctoral thesis development, if I'm not wrong. Did you plan in the medium or long time to validate your framework in a real industrial environment? Maybe it's something that you are a relevant environment, a controlled environment, or so on. Maybe something that you are thinking of.
Yeah, of
Talking
course.
about?
Actually, the main idea is that the communication protocol selected belong to in real industrial systems. OPC UA, it's a communication protocol that is wider known. And of course, the main idea is try to maybe to merge all the communication protocol requirements into a one just communication protocol that can support all the tasks from an industrial environment. Of course, this is very difficult because, as you know, different sensors and different proprietary or manufacturers, they have their properly communication protocol for their devices. But the main idea is try to translate all these requirements to a IoT communication protocol, open source, with the main features that can have, for example, OPC UA or DDS. I don't know if this responds your question.
Okay, yeah, sure. Okay, thank you so much again, Luis, and congratulations for your work.
Thank you.
So I think, if I'm not wrong, the next presenter is Fabiano Conumbano. It's okay. He's going to present the work Data Spaces and Blockchain as Enablers of a Sustainable Data Lifecycle in the Metaverse by Guido Pervoli, Federica Gentili, and Marco Gaglietti.
Okay.
Okay, Fabiano, we can see you, and also we can hear you.
Okay, I will share the screen.
Okay.
The presentation. Okay, one moment. Okay.
Okay, the screen is loading. We can see your entire PowerPoint window.
Okay.
Okay. Now is full screen slide. So whenever you want.
Okay. Thank you, Ricardo. Good afternoon, everyone. I'm pleased to present this research on behalf of Polito team and the NOUS project. As this is the final presentation of this session, so I will aim to keep it clear and fast. Okay, this work explores how an hybrid approach that integrates data spaces and blockchain technologies can support a sustainable data lifecycle in the metaverse. When we talk about the metaverse, we often focus on virtual environments. However, the metaverse is first a data-intensive digital ecosystem where data is continuously generated, exchanged, and transformed and reused across multiple actors and multiple platforms. Such dynamic environments raise critical challenges related to trust, interoperability, sovereignty, and the long-term sustainability. In this context, the NOUS project represents a flagship European initiative focused on designing foundational architectures and governance frameworks for a secure and fair data exchange in complex digital ecosystem. And looking at the current literature, we observe that data spaces and blockchain technologies are often studied separately, despite their potential synergies. In fact, most of the existing approaches remain fragmented, and there is a lack of an holistic perspective capable of governing the entire data life cycle. And this paper aims to address this gap through a brief literature review and by proposing an initial reference framework that captures the interplay between these technologies. As you may have already noticed, the framework is structured around the core 4 pillars: data spaces, blockchain technologies, sustainability of the entire data lifecycle, and data economy in the metaverse. Data spaces represent a key European instrument for sovereign and federated data management, and initiatives like Gaia X promote interoperability and governance by design. However, challenges remains, particularly in the dynamic policy enforcement and the life cycle auditing across different domains. Distributed ledger technologies provide complementary capabilities such as immutability, decentralized trust, transparency, and automated enforcement through smart contracts. But at the same time, they aren't suitable for storing large volume of data, or there are several challenges related to the energy efficiency, scalability, and privacy concern. Another fundamental concept is the sustainable life cycle, and in general, the data management sustainability. That this concept goes beyond the energy efficiency, but it includes governance, ethical governance, user consent management, and the responsible and reuse and long-term value creation of the data. And these require a sustainability by design approach aligned with the ESG principle. And within this perspective, an hybrid approach, an hybrid integration of data space and blockchain technologies enables a more balanced and resilient data economy model in the metaverse. Okay, the section 3 is this research context. And in a broader perspective, the NOUS is not only a technological matter, but also a political and strategic one, in consideration of the current evolving geopolitical landscape. In this specific research context, NOUS explores how data space and blockchain technologies can jointly support a sustainable data lifecycle in complex digital environments. And this work aligns with the project's foundational dimension, these three: the technical interoperability, the governance and trust, and the economic and social sustainability. Okay, now we see the roles of data space and blockchain in this project and in this architecture. Within this architecture, data spaces represent the foundational infrastructure across the technical, legal, and organizational dimensions, and they act as a central orchestrator of a federated digital ecosystem, ensuring sovereignty and interoperability. In the other side, the blockchain complement these infrastructures with providing the auditability, the traceability, and the automated trust mechanism through smart contracts and through immutable provenance records. And in this framework, blockchain function as a trust anchor, reinforcing transparency and verifiability across the entire data lifecycle. The reference architecture, this characteristic of data space and blockchain become particularly crucial in the multi-actor governance model environment such as the metaverse, where governance must balance between the decentralization and coordination. And the proposed architecture balance key requirements such as trust, decentralization, modularity, scalability, and sustainability. To make these, we made key design choices, includes a modular and a scalable structure, the separation between control and data layers, the governance orchestration through NOUS, the blockchain only for core trust services such as the notarization, and only for core the metadata, and a shared data space acting as a central orchestrator. Okay, and this figure show the architecture composed by 5 interrelated layers. And the first and the principal thing is that this model represents a modular, federated, and scalable infrastructure designed to be independent from a specific data space frameworks and capable of tracking any data lifecycle operation. At the top, there is the governance layers that ensures regulatory alignment and operational oversight. In this case, NOUS is the governance entity and isn't only a normative actor, but also a technical anchor. Under the governance layer, there is the blockchain layer that provides notarization and the cryptographic validation and independent auditable of data transaction between each node. The node, the consumer and provider node are represented in the flanks of these figures. And in our case, EBSI, the European blockchain services infrastructures, was selected as it represents the EU endorsed blockchain reference infrastructure. The central orchestrator is represented by the data space layer, a semantic.
Fabiano,
Yes.
you've got 2 minutes left.
Okay. A semantic and technical broker that harmonizes data access among all participants and directly interfaces with the blockchain. And below this layer, there is the API and middleware layer that enables interoperability between domain systems and the shared data space and triggering the blockchain operation where required. And finally, the domain-specific layer that includes the individual use cases implemented within this ecosystem. And for instance, the use case one is related to MASA and smart mobility, was previously presented by my colleague Marco Gaietti. Okay, this reference architecture supports a dual paradigm, centralized orchestration through NOUS governance and data space layer, and the decentralized execution through the blockchain layer. And this balance allows the system to combine efficiency, autonomy, and automation while addressing the complex requirements of a dynamic digital ecosystem. And in conclusion, these architectures provide a foundation for building a sustainable, verifiable, and resilient ecosystem in the metaverse, enabling integrated governance of the entire data lifecycle through the synergy between data space and blockchain technology. And as a final consideration, future work could explore how this architecture may be further specialized with different types of data spaces or different governance models or specific technical context. Thank you for your attention.
Thank you so much, Fabiano. A very interesting presentation for sure. Any of the attendees has any question for Fabiano? Okay, if not, I can ask one. What are you thinking about the scalability and also performance issues, when scaling this solution in a large scale metaverse environment? What about it? What about them, indeed? Maybe it's something that by the moment you are not thinking about, but only you have something in mind.
Okay, yes, the problem of scalability and performance is one of the core problems when we talk about the blockchain. And now we have made a proof of concept to experiment different solutions and to better improve the scalability of this architecture. with different solutions, like the separation of the layer, with a different blockchain layer, the layer 1 and the layer 2, to minimize the minimization. The goal is the minimization of the overhead within the blockchain, because represent a bottleneck of this architecture. And in ecosystem like the metaverse, where where the data intensity is a core matter, we make different experimentation to address this problematic. I don't know if I...
Yeah, I think so. Thank you so much, Fabiano.
Thank you, Ricardo.
Maybe another question from the attendants?
I interrupt the conversation.
Okay, again, thank you so much and congratulations for your work, Fabiano. Also,
thank you.
Before Gaetano is going to do the closing speech, okay, I want to congratulate to all of the speakers for the presentations. Celia, twice indeed, okay. Diego, Carolina, Marco, Luis, also Fabiano in this occasion, okay. Congratulations for your works, the speech, and all the authors. And thank you so much for participating in the conference. And I'm giving the floor to Gaetano from Korea University of ENA.
Thank you.
Because he's going to do the closing speech of the conference. And thank you again for all the participants.